So thanks for the introduction. As Christian said, I would like to speak about network verification today. So essentially internet networks. So I'm not talking directly about abstract networks. So today will be more practical than yesterday. There will also be practical sessions that I will try to intersperse in between, so probably during the second slot, where you will actually be able to play with an actual verifier. A simple one, but you will be able to play with some verification technologies there. So perhaps I would like directly to motivate why we need verification. And so this is an example from, I think, 2021. And perhaps some of you here are users of Facebook, Instagram, WhatsApp. I would imagine that's the case. And perhaps you remember that in 21, in October, there was a huge meltdown, essentially, of the entire Facebook infrastructure. So Facebook.com was down, WhatsApp, Instagram, all these services were down for many hours. And so that, when that things happened, that cost millions to a company like Facebook. All right. So when you read the postmortem, when you read that, what you see is that the engineering teams have learned that configuration change on the backbone routers, coordinating the traffic between the data centers, caused issues that interrupted this communication. So essentially what they made is a mistake as they were operating the network. They made a mistake in their data centers that caused the entire network to go down. It was so bad that they could not even enter the buildings anymore. So it so turns out that in Facebook, you have like access control on all the doors, and these are connected on the networks. And so when your network is down, you cannot actually badge anymore, so you cannot enter the rooms. So this is one of the reasons it took so long for them to debug these things, because they could not access the buildings anymore, and so the engineers were trapped outside, and they needed to find the keys, the physical keys, in order to open the door. So that, of course, caused a lot of, let's say, stir and reputation effect all over the world. I mean, Facebook is a worldwide company, of course. So the clicker is a bit finicky. So you had like many fun tweets, essentially making fun of Facebook and perhaps the lack of good network operation or problems happened in 2017, when Google broke allegedly half of the internet in Japan. So millions, I don't know how many people there are in Japan, perhaps 200 millions or 150 millions. So half of that could not access the internet for a few hours because of a mistake in a Google network. So here, it's a mistake that affected the border gateway protocol, and we'll speak a lot about this protocol today. That's the protocol that glued the internets together. It's the routing protocol that we use in the internet today. And a Google engineer allegedly, again, made a mistake while operating the Google network, and that mistake has an effect that they announced a lot of the Japanese prefixes that then started to transit through Google in Chicago. So you had this very weird path where traffic was originated in close to Tokyo, then was transiting in Chicago, and then back to Japan after, which of course reduced a lot the throughput that was available for the Japanese users. So that event only lasted a couple of hours, but it was so bad that actually the ministers, the government stepped in after that and said that this should never happen again. But of course, as we all know, this most likely will happen sometimes in the future. So closer to us, in Switzerland, there have been many examples. There are more recent ones, but this is one famous one that happened in February 2020. So this is one of the multiple problems that happened in the Swisscom network. And Swisscom, perhaps you know, but they have a mandate from the government to actually run the emergency numbers. So if you pick up a phone here and you call 114, I think in Switzerland, actually Swisscom is running this infrastructure. So they had, again, they made a mistake while operating the network, and the consequence of that all the emergencies numbers were not essentially available, again, for I think 1 or 2 hours. So these are calls that, I think everybody here understands that you really want to make immediately, right? So, so this possibly could have even life-affecting consequences. So it's much worse than just you cannot access Instagram, which is probably better for productivity. But here, actually, lives are at stakes. And overall, there have been studies that have shown that the majority, actually, of the problems we experience in networks are not due to physical failures, like you may imagine, but are actually due to you and I, humans, actually touching and breaking the network as we do so. So human factors are really responsible for the majority of the outages. So with this kind of like motivation, let me come back to network verification and synthesis. So there's been a lot of work nowadays in the research communities for the last 10 years, roughly. So roughly when I joined ETH, to quote Christian, where we try to verify, so proof properties about network infrastructures. And so here the situation is a bit like this. So let's say you are an operator, an ISP operator, so an internet service provider operator, and a customer is calling you and they cannot reach their favorite website, which happens to be our group website. So there is a problem somewhere in the network and essentially there is no reachability anymore. So the first thing that you could try to do if you are an operator, of course, is, well, you will check whether there is indeed a problem. It could be that the problem is at the customer level, right? Somewhere, for instance, in the, I don't know, the machine that the user is running, and not necessarily in the network. So one thing you can do, of course, is you connect yourself to one of the router. I mean, you will try to get as close to the source as possible. So typically, you will try to connect yourself to the router that connects the customer to your network, and then you will actually try to reach a website from there. For instance, you will use ping. And so then you will check, and for instance, you might see that at this point you have connectivity. That doesn't mean that there is no problem in the network. It could mean that there was a problem 5 minutes ago and then the problem is gone. You just don't know. At this point in time, at least, you have like IP level, network level connectivity. So the advantage of that method, which is arguably extremely simple, is that you are actually sending traffic through the network. So you will be excluding a lot of errors, if there are some, because you are really exerting the network. So routers are forwarding packets that you are sending, so you're testing a lot of things. The problem, of course, is that you did not prevent the problem from happening in the first place. So it's reactive, it's not proactive. And you also have very poor coverage. So you're really testing only a single pass in your network, and it could be that there is a much wider problem that you are completely missing. So the idea, of course, is we would like to help the operators preventing this problem from happening in the first place, okay? So we would like to avoid this misconfiguration from even having any consequences in the networks. So how can we do that? Well, a second try, which is still not verification, but it's better, is that you could run automated monitoring solutions in your network, and indeed many people do that as well, where you will have essentially, you will send probes across your network towards a subset of the destinations that you care about, and you will essentially check the liveness of these probes all the time. So the advantage here is that you will detect the misconfiguration as soon as they affect the traffic, provided that you have a good enough coverage. The problem is that you still won't prevent the problem. You might be very quick in detecting them. It might take you a few seconds, but the problem will still happen. And if you really want to have a good coverage, it will be very costly. So you will need to send the probes from technically all the possible ingresses in your network. And I mean, there are too many destinations in the internet to test them, all of them. So you will have to select anyway a subset, so your coverage won't be perfect. But still, it's better than just after the fact post-mortem testing of your network. So now I'm going up in the level of complexity. A third try that you may want to do is to actually try to simulate network behaviors on many, many different inputs, and then check that for any of these inputs, your network is actually correct. So now we are going more towards verification here. So you will have an ensemble of situations, case situations here, and then you will test in a simulator that your network is correct on all of them. And of course, if you test on all the situations, if you are exhaustive there, then you can actually go to the verification stage. So now what is interesting here is that for the first time, you are proactively testing your network. So if there is a problem in the simulation, you will actually find it before hopefully that problem has happened in reality. So this is good. We are like now proactive. The con is, at least if you're not careful, it's hard to provide guarantees about, let's say, the coverage of your test. So you need to think about the situations that you want to exert your simulation thing. And then you also need to be careful about, let's say, the precision of your simulation. So when you are running real routers, they have a given behavior, and you need to simulate that behavior. But if you think about the control plane of a router, these are like complex operating systems with millions and millions of lines of code, and so simulating that is hard, okay? So there is also like possibly you might actually miss some mistakes. You might have false positive or false negatives just because your simulation is not exactly precise. But still, it helps to detect proactively problems. Correct, yes. So here I'm assuming indeed that you know what is your network topology, that you know your configuration, that you know also the kind of like inputs that your network may receive. Yeah, you know. So you are one of the operator of the network. You have full access to your network. You know everything essentially, and you have control over your network. So indeed, you cannot verify someone else's network. That wouldn't work. Yeah.
Is this different from fuzz testing?
Not really. At this point, I haven't really defined like the different situations, and now we pick them. So you could kind of like randomly pick situations and try to test the simulator with the simulator using fuzzing. I mean, there are many kind of like flavors of verifications that people are using. We try to have full coverage, so really to reach like guarantees. But fuzz testing would be one technique you could use to actually pick the situation. So it's not different, it's included, yes. So this is actually a good transition to this question that will occupy us for a good part today is how can we guarantee reachability? So the property that we care about, the base property that we care about in networking is reachability. We want to make sure that when you send data through the network, the data will arrive eventually to the destination without simulating all the possible scenarios, okay? So because that, of course, doesn't scale. And so this is where network verification will enter into the mix. So verification, if you think not only about network verification, but also program verifications, for instance, the idea is to really provide a guarantee that the system fulfills its specification. And so specification is a formal property about your network in this case. And this property, you want it to be true in a universe of environments. And so here I have to define what I mean by environment. So a network evolves in a current environment. So what is the environment is, for instance, the status of the links. So some links may be up, some links may be down because of failures. So that's one aspect of the environment of a network. And another aspect of the environment of a network are the routing inputs that the network will receive from its neighbors. So as you know, and I will do an introduction again to routing in a second, but the network in the internet is not alone, okay? So networks are connected to others, and so they exchange messages. And so the messages that you receive from your neighbors, you don't control them directly. So there is an uncertainty about these messages that you will receive, and so you want to make sure that your network will be correct for any possible messages that you will receive from your neighbors. And you also want to make sure that your network will be correct for any possible link failures that you may have, okay? So these are the environments we care about today, link failures and routing inputs. The kind of property that you care about in our world are, as I said, like reachability would be an example of one, so routing and forwarding behaviors. You might also care, of course, about security policies. So very, very common, for instance, if you have firewalls, you want to ensure that all your traffic will eventually cross a firewall, for instance, that you will never bypass a firewall. So these are very common security properties. You may want to ensure isolation between different hosts. So perhaps you don't want some hosts to access some critical nodes, perhaps a database in your network that you want to protect. So that's an isolation policy, for instance. You may care, of course, about performance, and this is much harder, but you may want to be able to verify that your network will never be congested, that there will be some kind of like average throughput that will be available at all times, that you will not experience packet loss, et cetera, et cetera. So these are actually much harder to verify, and actually Patrick, I think, will speak about network calculus that tries actually to answer more specifically these questions. I won't talk so much about performance, but that's also something you may want to verify. And then there are plenty of other properties that you may want also to verify. A common one is convergence. So I don't know if you know this, but it's not guaranteed that the network will converge to a steady state, depending on its configuration. So you may, for instance, want to verify that your network will actually stabilize at some points given the inputs. So these are also properties that people care about. As I said, the environments that you want to check these properties in include external routing inputs, failure scenarios, possible traffic demands, etc. Questions? Yes? Steady state, I mean, that's the state the network will eventually reach once it has finished to converge. So for instance, let's say you have a network, everything is stable, a link goes down. So a network runs a distributed algorithm, a routing algorithm, and so that routing algorithm will need to do its job to essentially move the traffic around the failure. So that will require some steps, and so eventually, hopefully, these steps will finish, and then you will end up with a network that forwards around. If the network diverge, then it will forever kind of like exchange messages and never stabilize. That can happen. It's a bit twisted, but that can happen, and so you may want to verify that this does not happen in your network. That's steady state is the stable state you eventually reach. Yeah.
So you assume failure scenarios are equivalent to attacks?
No, not at all. So I'm just assuming that your network is actually not under a malicious threat, but I mean, it's just a physical network where anything can fail at any time, and eventually everything will fail at some point. And so you just want to make sure that if something fails, the property that you care about still will apply. So this is why, of course, in an ISP, for instance, or in data centers, you have many parallel links, so that if any of them fail, you still have connectivity. So network topologies that do contain a lot of redundancy to protect around failures. But if you have like fancy policies like firewall, for instance, it could be that when a link fails, your network converges around your firewall, for instance. And so you want to make sure that even if there are failures, you are still correct. So that's what I mean. Of course, you could include an adversary here as well. It doesn't really matter who is creating the failure, but I'm not assuming adversary per se. Yeah. So essentially, you end up with kind of like spectrum here, right? We start with validation, which is just kind of like testing. And so here, I test with essentially, clicker, yes. So you can test with simple pings, then you kind of like go to monitoring, where you will test from more sources in the network. Then you go all the way to a proof, where you can actually say that for all possible inputs, for all possible environments, your network will be correct. And then in kind of like in between, you have like the simulation case. And so how green you are depends essentially then on how many environments you are exploring, up to the point where you are exploring them all. And of course, I mean, this is not a surprise, I guess, for any of you, but the more you try to go to the right, the more costly it will become in terms of scalability. The more like test, for instance, environments you will have to explore. Hence, the reason to try to not have to consider all of them individually, because of course that completely explodes. So verification, the kind of like way to understand this, the kind of like input-output that you have. So you have a network topology. So this I'm assuming you know, again. You have all the configurations of every single device in your network. You have the specification that you want to verify. And then you have all these environments. So these link failures, these routing announcements, etc. So this is the input that you give to your verifier. And then the job of a verifier is actually simple if you think in terms of its output. It needs to give you a green thumbs up. Everything is okay. Your network is correct, guaranteed. Or, if it is not the case, it should return you a counterexample. So a counterexample in our world is an example of an incorrect environment in which essentially your network is doing the wrong thing. So for instance, it will be, in the case of a link failure, it will be an example of a link failure that will make your network, for instance, bypass your firewall. And it will be a concrete example that as an operator you can look at and then understand what is the problem. So that's kind of like typical in verification technologies. Same thing in a program verification. If you have a property about, I don't know, like some loop invariance, for instance, and you have a counterexample, so it will be a concrete input to your program that leads your loop invariance to be violated. So same ideas here that apply in network verification. So now when you as an operator, when you get this counterexample, your job ideally should be to actually correct your configuration. So well, I'm assuming here you can correct the problem using configuration. It could also be that you need more links or you need to change the topology. But let's say today we'll speak mostly about changing the configuration. So kind of like what Facebook kind of like did, it changed its configuration. So you need to figure out, and there is definitely a challenge here. So from this concrete counterexample, you need to figure out how to change the configuration in order to fix the problem. This is hard, so it's not like verification is a panacea, because even if you get to the counterexample, you still need to fix the network. And one of the problems is that there is kind of like a semantic gap between the concrete counterexample that you get and the configuration that you will need to fix. So these are not at all the same world. Okay, so here we're talking about routing protocols, and here we're mostly talking about traffic flowing in a graph. So as an operator, you need to bridge this gap, which is not always easy. So an example of a mistake doesn't tell you the fix, essentially. Okay, it just shows you where the problem lies. So this is one issue. A second issue, which is complicated for operators, even with a counterexample, is that the specification of a network like Deutsche Telekom, Swisscom, AT&T is extremely complex. So it's much more complex than just reachability, okay? So as an operator, you need to keep that in your head, the entire specification, in order to figure out how to fix your network so that it's correct with respect to the specification. We have been actually mining specification in actual network, and we ended up in reasonably simple network with more than 10,000 predicates. So just again, like, it's something hard to keep in your head as a human. And then, of course, the more fancy your objective, like if you're talking about performance objective, it's actually a very hard optimization problem to optimize your network for performance. So it's really not easy. So all this to say that verification is kind of like a first step, but kind of like the ultimate destination in verification technology is the synthesis destination. And that also applies to programs. So there have been decades of work on program verification. I give you like a piece of C code, and I want you to be able to say that this C code is correct. But more recently, there's been also a lot of work on program synthesis, where, for instance, you want a sorting algorithm which is fast, and then you say this, and then automatically you get a sorting algorithm in C, for instance, which actually is correct and is fast as well. So it's kind of like the holy grail in computer science, as it has been said many times, where you automatically generate code that is actually correct and, for instance, efficient. So in the world of network, in configuration synthesis, what we have is now we have kind of like different input outputs. So we still have a topology, we still have a specification, and we still have a set of environments. We give that to a synthesizer, and now the synthesizer will output a configuration for all the nodes in the network that guarantees that the network is correct. So if we have a synthesizer, then the Facebook problem would not have happened in the first place, okay? Because Facebook would have been able to produce a correct configuration directly using the synthesizer. So the kind of like synthesizer kind of like subsumes verification, if you want. If you have a synthesizer, you don't need verification anymore. And again, like the problem of synthesis, to find a configuration, not to find a counterexample, to find a configuration that satisfies the spec in all the possible environments. So it's a much harder problem, and it generalizes verification. Yes, so here, of course, if the synthesizer is complete, it's guaranteed that you will find a solution. Not all synthesizers are complete because it's a very hard problem. You have like the space across the space of the universe of all configurations you want to explore is gigantic. So this is, of course, a very hard problem to scale, not surprisingly. But if you can do that, then you can do things like automatic configuration repair, intent-based networking. That's kind of like the dream, whereas I was saying, you just declaratively tell me what you want your network to do, and then I will automatically produce your config that does that. And of course, you can use that for optimization as well. So today, in the rest of the lecture, I will speak about the verification. I will tell you essentially how do most verification, network verification technologies work today. We'll play with like the main solver technologies that supports that. And then I will also speak about network synthesis and how we can enforce network correctness. There, I won't have the time to dive in detail in both. So here I will be a bit higher level, but I will still want to give you the intuition about how synthesis can be made possible. And so I will also spend a little bit of time there. So two parts, very first, and then synthesis after. And before I go there, though, as I said, I want to make sure that you understand what I'm talking about when I speak about routing protocols and BGP in particular. So perhaps just a quick show of hands, who has never heard of BGP in the past? Okay. It's not a problem, right? I just want to know, okay? So a few people. So I will quickly go through that. I hope it won't be too long. But essentially, I think it's important anyway, if you have heard of it, that you get a refresh, because you will have to play with a verifier for BGP configuration. So it's important to know what we are talking about here. So if you look at the word internet, there is inter in it. And it's because the internet is really, by definition itself, a network of networks, okay? So in the internet, we have this protocol, the Border Gateway Protocol, which is the main routing protocol that supports it. So the way to think about the internet is to think about a network of networks that are known as autonomous systems, or ASs, okay? So you have AT&T is one, Deutsche Telekom is another one, Swisscom is one. Each AS has a number, which is an AS number, an identifier for that AS. And then essentially BGP is kind of like the glue that holds all these ASs together. So it's really like a good way, I think, to think about BGP as a gluing mechanism between different networks. And so Deutsche Telekom speaks BGP with AT&T, for instance. AT&T speaks BGP with Swisscom. And so this speaking is used in order to exchange information about destinations that are reachable in these networks. And of course, in the internet, we talk about IP prefixes, IPv4 or IPv6 prefixes that are being exchanged over these BGP sessions. So using BGP, for instance, you will have the ETH network that will advertise to its neighbors, Swisscom and AT&T in that example, that it is hosting one prefixes here /16. So if we want to reach this /16, you can actually, you should send the traffic ultimately to ETH. And as you can see in BGP, there is this notion of path, which is important. So BGP is a path vector protocol. So all the BGP message will contain the path that the message has taken. So of course, the origin only contains a single element, so the AS number of ETH. And as this path will, as this BGP message will propagate, the path will get longer and longer. So for instance, here, when AT&T advertises this routing announcement to Deutsche Telekom, then the path will be 1040. So in BGP, by convention, the origin is always on the right, and then you happen on the left. So BGP can, oh, sorry, questions, yes.
I remember there were these prefixes. Are there still only these prefixes that are advertised in routing? I thought this has become way too complex now to manage all those things. It was my impression at least, because it's so fragmented. It's not like there is one network in MIT and one in ETH Zürich and that's it.
Sure, correct, yes. So it's still only prefixes. Of course, now you have IPv4 and IPv6 because there are not enough IPv4 prefixes anymore. The problem that you are like referring to, the fragmentation, is still very much present. That's why, as of today, we have, I can even check that live, CIDR report BGP. We have almost a million of IPv4 prefixes in the BGP table. And this is the number of ASs. We have 75K ASs. And to that, we need also to add the IPv6 prefixes. So we are way beyond 1 million now, yes. So, so we are like 1.1 million at least prefixes in the BGP tables, yes. So this is something I will not speak about, but of course people have been looking also at ways to compress and aggregate this information. There are works on that. We have been working on this as well. There are solutions, but they are not deployed. But I mean, BGP has been surprisingly good, I think, at scaling to these levels. It's not like the internet is crumbling at some point. So we are still, I think, way within like the normal operating regime. But of course, it does create some challenges. Like convergence, for instance, takes longer when you have many, many prefixes. But we have not moved beyond destination-based forwarding in the internet yet. Yes, so it's still prefixes, as you said. Other questions? All right, so if you are a BGP router, your life is made of 3 steps. So it's pretty boring life. You receive routes from your neighbors. You select one best route, and then you export this route to your neighbors. That's what you do all day long, forever. Yes, it's a very important life, but a boring one. So in BGP, it's a policy-based protocol. So what it means is that these different ASs, these different networks, they are free to configure their routers in order to prefer some advertisement over others. So this is very important in BGP, and that allows to implement economical business relationships, okay? So each AS, each network in the internet is free to select and use any path it learns, okay? And typically in BGP, the way I'm teaching my students is to tell them that they should think that in the internet we try to minimize the cost of sending the traffic to the destination. So BGP is kind of like the follow the money protocol. Traffic is flowing alongside the cheapest path, not necessarily the most performant one. So sometimes in the internet, the reason why you have bad performance is just economic in this case. So each AS is free to select and use any path. So this is one aspect. So for instance, here, Skynet, here, this former Belgian network, we received 2 paths to ETH, one via AT&T, one via Deutsche Telekom. As you can see here, the path via Deutsche Telekom is longer. It has 3 hubs because it goes here, here, and there, while the path via AT&T only contains 2 hubs. But still, Skynet is totally free to actually take this path over the other one. So there is no mandate in BGP to pick the shortest path, not at all. You pick the one that you like. As long as you receive it, you can pick it if you wish to do so. So for instance, it could be that for here, this network is much cheaper to use this link than to use that link. And so they will just prefer this path over this other one. So again, this is very common in BGP. So each AS is free to take any path, and each AS is also free to export this path to their neighbors or not, okay? So they have also full control about to whom they're advertising this path further. And of course, here you have to think about when, let's say we are 2 BGP routers and we are speaking BGP with each other, if I'm advertising you a prefix, I'm kind of like giving you the right to send me traffic to that prefix, okay? So if I'm not sending you a prefix, then essentially I'm sparing myself from having to carry your traffic. So this is why here there is this kind of like bias towards not sending, because if I'm not sending, then I'm not carrying, I'm not having to pay the cost of like carrying your traffic to the destination. So again, in a logic where you're trying to minimize your cost and maximize your revenue, you will try to avoid sending prefixes to people or to networks that will cause your cost to go up. So this is again something important to keep in mind in the future. So, yeah.
So whenever a path is received, what kind of check is the AS doing? Whether the path is valid or someone has injected an invalid path?
Yeah, so there are like different checks that are done. Like by default, the simplest check is to look at this content of the path. And so each AS has a number, and then one check that you do is you check that you are not already in the path. So that allows, for instance, to check for loops, and then you will remove automatically all the loops. So this is one check that routers do. By default, the original BGP, the vanilla BGP, does not constrain anything about what is the content of the message. So you did not have any security about who can originate a message, who can originate a prefix. That created all this problem about BGP hijacks that we have today. So now things have been changing, and there have been like secure version of BGPs that are being rolled out with success. So one of them is known as the RPKI. And so what that extension of BGP does is that it allows an AS to verify that the origin of the path is legitimate. So each AS has access to a big database that record the mapping between a an AS number and the prefixes that that AS number can advertise. So for instance, ETH in the database will be associated to this /16. And so when I receive this prefix, I can check, okay, this is a prefix that comes from AS40. Is AS40 allowed to advertise that prefix? Yes. But if Deutsche Telekom would be to advertise that prefix without the ETH number, then I can filter it out as being essentially a problematic announcement. So this is the second example now of checks that is done, is to check the origin of the path. So this is another example. Otherwise, there is very little which is actually being checked on these messages. So besides the origin, you can still tamper with the rest of the path. You can, of course, tamper with the prefixes. And there are like 10 other different attributes that can be tampered with. So BGP is surprisingly brittle when it comes to security, even with our PKI in place. And it's surprising that it works even in the internet today, but you have to also keep in mind that the attackers, they have an incentive to also have the internet working, otherwise they cannot reach their targets anymore. So it's kind of like counterintuitive situations in which also the attackers, they don't want to destroy the internet. And also, in order to inject BGP advertisements, of course, you need to have access to a BGP router. So it's not something that I can walk here, for instance, and then suddenly start to inject BGP message. You will need, for instance, to access, I don't know, like the Swisscom network, for instance, or like a border router in your ASs. And this is not something that is easy. And yeah. Yeah, yes, yes.
Where is this stored?
Where is this what?
Where is this trusted database?
Ah, right. So this is maintained by essentially the same organizations as the one that is allocating IP prefixes to different networks. So you have like, in the internet, you have kind of like a hierarchy that exists to assign essentially addresses, DNS names, and essentially certificates about who is owning, who has the right to advertise a prefix. And so this is the same organization there. So it is centralized, but it's non-profit. It's based in the US, but it's better than nothing, though. So it is something that is definitely valuable. So you have like these regional entities, like you have one in Europe, one in America, South America, Asia Pacific, that essentially get delegated the rights to issue these certificates from this central organization, the IANA. So that's the one, this... Yeah, correct, yes. I mean, there is no reason why you don't want to disclose that. Yeah.
Maybe, yes.
But then you can use private prefixes within your own network. You don't have to say that you are using some fancy prefix inside if you don't want people to know. The reason why you want to disclose that is that these prefixes, I mean, they are running internet services. So the idea is that you want people to be able to access your internet services. If you are running some top secret Swiss thing, you don't need these prefixes to be accessible from the outside world. You don't need BGP at all. You just don't advertise them in BGP. Yeah.
You just need to be brutal.
Yeah. Yeah, of course, then you can think about, for instance, overlay networks, as was mentioned yesterday. If you want to enable islands to still access your fancy network over the internet through tunnels, for instance. So that is also possible. But here I'm talking really about public internet, publicly accessible IP addresses. Yes, I'm not talking about more private consideration. All right. So as I was saying, like two things again, like an AS is free to pick any path that it receives as best, and an AS is free to export or not export a path that it receives to any other neighbor. So for instance, it could be here that Swisscom chooses not to export the routes that it receives from ETH to AT&T, and that effectively is a do not enter sign, okay? So by doing this, Swisscom do not allow AT&T to send its traffic to reach ETH, okay? So AT&T will have to use its direct link because it doesn't learn an alternate path via Swisscom. Okay. All right, so going a little bit deeper now in BGP, because again, you need to understand a few things about it to know how to configure it. But essentially in BGP, you have two types of sessions. You have the sessions that are external. So these are really the sessions that run between different networks, like here, Skynet and Deutsche Telekom, and well, this network in the middle that doesn't have a name, Swisscom ETH, etc. So these are like external BGP sessions, eBGP sessions. And then you also have iBGP sessions, internal BGP sessions. And these are sessions that are established between the routers within a single network, okay? So these BGP works on top of TCP, and so you have TCP connections that are established between all the routers. And using these iBGP sessions, the routers will propagate the routes that they learn from the exterior. So for instance, if Seattle here learns a prefix from its neighbor here for that destination, this /16, it will use the iBGP sessions to propagate this information within the entire network. And that allows, for instance, the router in Atlanta over there to learn that it can reach these /16 prefixes via Seattle. And then it can use another routing protocol, an internal routing protocol, to figure out what is the path that it needs to take to reach Seattle. Okay? So BGP allows you to learn what is the egress point in your network. So the egress point here is Seattle. And then all the routers internally, they will use an internal routing protocol like OSPF or ISIS. I hope you have learned this protocol as well, based on shortest path routing typically, in order to guide the traffic towards this egress point, okay? So you always have in the internet kind of like two routing protocols, two family of protocols that are intertwined, interior gateway protocols, and then BGP running on top. Yes, and then of course, so essentially the life of a BGP route is that it goes on an eBGP session, external BGP sessions, gets propagated internally in iBGP sessions, and then gets propagated again on eBGP sessions. So you have this sequence of eBGP, iBGP, eBGP, etc. Okay, so that's kind of like how it works. Okay, on the wire, BGP is extremely simple. It's a very, very basic protocol. The most important things for you to know is that there is the most important message in BGP is an update message, and the update message essentially contains the information about this destination, these prefixes, plus other attributes that you can use in order to make a decision. And you send an update whenever you learn a new route. There is an update to a best route, or there is a removal of a route as well. So of course, sometimes there are failures, some destinations are not available anymore, then you need to withdraw this information as well. So an update can be positive. I know a new path to a destination. An update can be negative as well. I'm not able to use this path anymore, so you can kind of like move the traffic away. And so these attributes that go along with the prefix, so you have the prefix always, and then you have a bunch of attributes. So these attributes, they describe the route properties, and they are used in order to select and export, and they can be local or global. So the main attributes that we'll care about in today's lecture are the path, the AS path. This is the path that contains the ASs that have been crossed, mainly used for loop avoidance. And then the local preference is the other one. And this is just an integer which is attached to the route that tells how preferred that route is, okay? And so the higher, the more preferred. So these are the two main attributes that we'll consider. There are many, many more. Actually, this slide is not exhaustive. So if you want to understand BGP fully, you need to look at the other attributes, but today we don't need to go beyond these two attributes. So as I said, the AS path is just the list of ASs crossed, and it increases in size as you propagate the route. And then the local pref is an attribute that is set at the border of the network, and it represents how preferred the route is. So again, like now we put ourselves in the shoes of an operator configuring a network. So we are the ETH network here, and we have two providers, Swisscom and Deutsche Telekom. So these two providers, they provide us access to the internet. That means to all the destinations in the internet, to the 1.1 million destinations that are there. And so you can send all your traffic to Swisscom or all your traffic to Deutsche Telekom or a mix of both, okay? So as I said, like in BGP, what people tend to do is that they tend to prefer the cheapest alternative when there is a choice. And so let's say Swisscom is more expensive than Deutsche Telekom. So in this case, ETH will set a higher local pref on the routes that it received from Deutsche Telekom versus the routes that it received on Swisscom. So as you can see here, ETH will configure that router to set a preference value to 100, and this router, which is connected to Swisscom, to set a preference to 50. So that means that all the 1.1 million routes will hit these two routers. These two routers will attach preference 150, and then these routes then will continue to propagate within the network, and then in BGP you prefer the highest preference over the lowest preference. So this means that the traffic eventually will leave via Deutsche Telekom because 100 is better than 50. So all the traffic to all the 1.1 million destinations will take this path in the network and leave via Deutsche Telekom. Even though you could also have taken this path, it's not the case. So this is something that you have to configure as an operator, okay? You need to figure out the preference values, and you need to go on the router and essentially instruct it to attach these preference values to the route it learns, okay? So this is something that you have to figure out as an operator yourself. And of course, you can get it wrong, and then when you get it wrong, you can have knockout effect, of course, on your forwarding path, right? So if you set these values, you put like a 0 too much here, of course, suddenly all your traffic will shift and will go to Swisscom. So like really just like a single digit can have a knockout effect on your traffic. And so as I said, like these attributes, of course, they are used in the selection and export decision. So this is why they are being there actually. So this is the decision process that the router uses. So router, again, like the life of a router, boring one, you receive routes, select one route and export. How do you select? Well, if you have multiple routes to one single prefix, you will prefer the one with a higher local pref. So let's say we have 10 routes in total. We look at the ones with the higher local pref. There are 5 routes with the higher local pref of 200, let's say, and then all the others have a pref which is less than 200. So we throw them away, these 5 other ones, and we only keep going through the process with the 5 routes with a local pref of 200. Then amongst these 5 routes with a local pref of 200, we need to make a decision for one. So the next stage there is to pick the routes with the shorter AS path length. Okay? So amongst these 5, if we have, let's say, 2 routes with an AS path of length 2, then 3 routes with an AS path of length greater than 2, we'll throw these 3 away, and then we'll only keep now these 2 routes with an AS path of length 2. And then I won't go into the details of the other steps because I will need to introduce the other attributes that I haven't, but essentially there is a tie-breaking decision at the last step that ensures that you will always end up with one single route that you prefer for any prefix. So BGP is a single pass protocol. So even though there are many, many paths in the internet, each router only uses one to reach a destination. So that's also kind of like a limitation perhaps of the current protocols. And there are of course many discussions now about how to go multipass, but this requires extensions to the routing protocols that they are not there, not deployed yet. But again, like for this lecture, keep in mind that you first prefer the highest local pref and then the shorter AS path. These are the 2 main steps that we'll use today. All the rest we don't care, and then there is a tiebreaker at the end. So that's it. Yes, and then the last thing that I will introduce, and then we can go back to verification, is what I said about this business relationship. So the internet topology is really shaped around money, around economical and business relationships. So 2 ASs, they don't establish a BGP session unless they have some kind of like business relationship between each other. Okay, so people don't can just for the fun of it establish BGP sessions and then carry the network. So typically there is of course like a contract which is being established first that rule over the communication and then the forwarding of the traffic. And there are 2 types of relationships. main two types of relationships in today's internet. The first one is customer-provider, and then the second one is peer-peer. So customer-provider is essentially like you and I being private customers at our place. So perhaps you are like, if you are in Switzerland, you are with Sunrise, Swisscom, Salt, UPC, whatever. So these are your providers. You are paying them to access any possible destination in the internet. Likewise, Swisscom is allegedly the customer of Deutsche Telekom. So Swisscom is paying Deutsche Telekom in order to use Deutsche Telekom to reach all the possible destinations in the internet. So they have a provider-to-customer relationship between the two of them. So that means Swisscom is paying for all the traffic it sends to Deutsche Telekom, and Swisscom is paying for all the traffic it receives from Deutsche Telekom. It's a much more complex contract than just a flat fee as you and I are paying at the end of the month. So it depends on the amount of traffic which is being sent. Usually they take the 95th percentile rule, so you are billed based on the 95th percentile of the amount of traffic you have been sending over 5 minutes. And this is kind of like put in a contract, so we won't go into the details there, but at the end of the day, just think that the customer is paying its provider to reach the internet, and for the internet to reach itself. That's relationship number one. Relationship number two, peer-peer. So here, it's a relationship which is established between two networks that are, let's say, of similar size or power in the internet. So for instance, Swisscom is much smaller than Deutsche Telekom. So it makes sense that Swisscom is the customer of Deutsche Telekom. But Deutsche Telekom and AT&T, they are roughly equivalent. Both of them are tier ones. So they are sitting at the top of the food chain in the internet hierarchy. And so they tend to establish peer-to-peer relationship instead. Okay? So like Swisscom, for instance, would establish, you would expect Swisscom to establish a peer-peer connection with Sunrise because they are roughly at the same level. And so what is a peer-peer relationship? It's just a relationship in which you don't advertise all the prefixes of the internet towards the other. You essentially advertise your internal prefixes and the prefixes that you can reach from your customer. So essentially, you advertise to the other the prefixes that make you gain money. Okay? So because your own customer, when they send traffic to you, you gain money. So it makes sense that if you send that prefix to AT&T and AT&T starts to use you, you're happy because you are gaining money. But if Deutsche Telekom would have a provider and it would send that prefix to AT&T, then Deutsche Telekom would start to lose money. Okay? So peer-peer, you have to understand them as kind of like a restricted relationship in which you only advertise a subset of the routes, your internal routes and your customer routes. And the idea on the peer-peer relationship is that you do not pay the other one. So you essentially put the cable there. You have your routers. You will provision them. You will establish the sessions. You put the fiber, for instance, there. And then you exchange traffic for free after that. But you do not exchange traffic for all the destinations in the internet, only for a subset of them. So this is very typical, for instance, also with content providers like Netflix, if you think of it. They will try to establish peer-to-peer sessions with as many networks as possible. So they are like literally establishing thousands of peer sessions across the globes so that they can reach, for instance, Deutsche Telekom directly instead of having to go via a provider to reach Deutsche Telekom. So that means then they don't have to pay money in order to send their bytes. So you have to understand, for instance, that Netflix in the US at peak time is responsible for the vast majority of the bytes moved. So it's insane, the amount of traffic, right? So it's really something that they can save a lot of money by establishing peer. And it's not only in the US, I think also now in Europe, they are driving at peak time for sure. I think perhaps Netflix and YouTube and I don't know, Hulu, Twitch, whatever, but clearly video is ruling over the majority of the traffic at peak time by far. And it's not going to change in the future, that's for sure. All right.
Sometimes you read that essentially not that kind of video traffic that drives income. It's more like all
Yeah, sure. I mean, I'm not commenting on the content of the bytes that are being. It's just video content, but yeah, video is for sure like responsible for the majority of the internet traffic. And what is interesting, and that has happened recently, I was talking about this yesterday, but now, so if you think that this is Netflix and Deutsche Telekom, so now Netflix is even going a step further, is that not only do they establish peering sessions with everyone, but they actually ship servers to the ISP, so to Deutsche Telekom. Then Deutsche Telekom receive these servers for free, and then they install them within Deutsche Telekom. And these are cache servers. And essentially what Netflix will do is that during the night for Germany, they will essentially download their video onto these caches within Deutsche Telekom. And then when you go on netflix.com, you think, you are, I don't know, accessing a video which is stored in Netflix. But actually, it's not true anymore. Most of the cases, you are accessing a video which is directly located in the ISP. So if you are a Swisscom customers, that's for sure. Most of the video are stored within Swisscom. So they have many caches in Zurich and Geneva. And what happens is that you connect to netflix.com. This is Netflix. You are actually reaching the data center of Netflix there. And then they will see what is the video that you are looking at. I don't know, the latest episode of a popular show. And then they will give you a URL, which is actually stored within Swisscom. And then you will directly connect to that. So then it becomes very interesting because now these peering links, they only become used to prefetch the video content during the night, for instance. But the actual video traffic is flowing directly from within the ISP onto your clients. So that creates a new dynamics. And it's not only about Netflix, but Google is doing the same, Cloudflare, Akamai, all the bigger CDN are doing the same. So it becomes interesting for an ISP because now they have all these servers that are located within them that are controlled by someone else and are responsible for the vast majority of the traffic. Again, so now you end up with an internal traffic engineering problem versus an external traffic engineering problem. So that kind of calls for new research in the area. But so if you are interested, you can check. In Netflix, it's called the Open Connect program. So you can see they're quite open about it, of course. All right, so almost done now with BGP, only a few slides left. But essentially, as I said, these business relationships, they conditions route selection. So whenever you have multiple paths to a destination, multiple routes to a destination, you would prefer the ones coming from a customer over the routes coming from a peer over the ones coming from a provider, okay? So it makes sense, again, economically. So if you can reach a destination via a customer, you gain money, right? So the customer will pay you at the end of the month. So it makes sense that you prefer that path. If you can reach a destination over a peer, you don't pay money at least, so it's neutral. And if you have to reach the destination via a provider, you pay money this time. So you lose money in this case. So it makes sense, again, that you prefer gaining over not losing over losing. So that's why you prefer this path that way. And then the export, you end up with a matrix, which looks like this. So the routes that you learn from your customer, you will export them to everyone. So if you are my customer, you are paying me for giving you access to the internet, okay? So I need to advertise your destination to everyone on Earth because you are paying me for accessing the internet. So I have to send these routes to everyone, independently of their type. But if I learn a route from a peer or a provider, I will only advertise that to my customer, okay? So I will only advertise these routes to the neighbors that are paying me for the traffic. So for instance, you don't provide a route, you don't provide connectivity between your providers, which would be extremely bad. So if you think about ETH being here, it has two providers, Deutsche Telekom and then Swisscom. Let's say you have Google here. And then Google is advertising a prefix, let's say 10/16 here. That's Swisscom advertised to ETH as well. So let's say you have ES1, ES2, ES3, and ES4. So here the route will have an ES pass 1, 2, and here the route will have an ES pass 1, 3. So what you can do, if you mistakenly configure your network, and that has happened many times in the past, is that ETH might make a mistake and essentially redistribute the routes between the two. So let's say Deutsche Telekom send the route here, and then it will be propagated back to Swisscom. So then the espace here will be 1, 2, 4. So Swisscom is very happy now. Swisscom has learned a route for Google via a customer, ETH. So Swisscom essentially now can learn to reach Google via this path. And now ETH is getting screwed completely because it's paying for the traffic it receives from Swisscom, and it's paying for the traffic that it sends to Deutsche Telekom. So this is why you never provide transit between two providers, because you're paying for the traffic, you're paying twice for the traffic. That's one issue. And then the second issue, as you may imagine, ETH is a small fish in the internet, an important but small fish. So the available throughput that you have here is really ridiculous compared to the amount of traffic that a network like Deutsche Telekom would exchange with Google, okay, or Swisscom. So if Swisscom was to start using ETH to transit traffic for Google, it would send all the traffic into a really small pipe. And so you will have massive congestion. That's exactly what happened in the example I was mentioning, if you remember at the very beginning with Google and Japanese traffic. They essentially screw up their BGP policies and made the traffic take a very small capacity pipe. That, of course, created congestion, and that congestion then led to all the disruptions. But again, it's very easy to shoot yourself in the foot because these are finicky configurations to be made. And most of them, unfortunately, are made manually. All right. How am I doing with time? 15 minutes, okay. Until some breaks. So I guess then I can start speaking about verification, and then we can just have the break. So so now you understand, hopefully, or you re-understand how BGP works. So BGP, you need to configure these routers in order for them to select the right routes, in order for them to export the right routes. And you do that on a per router basis, okay? And so now what we look at is how we can actually verify that these configurations that you are like establishing are correct, okay, for some properties. So we'll use a concrete example just to start. So this is a very simple network. As you can see, we have 4 routers, 1, 2, 3, 4. This router here is connected to a provider. This router here is connected to a customer. So again, it should already ring a bell now that you should always prefer the routes from a customer over the route from a provider. You know why now. The configuration is the most classical configuration you may think about. There are no, actually right now there is no configuration about preference. This is what this route map means. There are no route maps, no filters, no preference. And then you have IBGP session between all the routers, a full mesh there. The specification is that you should prefer the route from the customer over the route from the provider for business relationships. And then the environments that you want to consider is all the possible routes that you can receive from the provider and the customer, okay? So essentially here it's a network where there is no configuration about selection, which is in place. So of course this is incorrect, okay? So if you run this network, it could be that the provider routes get preferred over the customer route. So the idea is that if you put that into a verifier, the verifier should be able to check that. So the verifier here, one counterexample it should be able to give you is that it should give you essentially a counterexample, which is a concrete set of routes that are incorrect with respect to your specification. So a route which is incorrect with respect to my specification means that it's a set of routes such that the provider is preferred over the customer, okay? So that's what I want as a counterexample. So here you can see an example where you have like a route for 10/8 that is learned at the provider here and here on the customer, or advertised by the provider and the customer. So B receives it and C receives it. And you can see that the route on the provider has an AS path of length 1, and the route on the customer has an AS path of length 2. And that indeed will mean that since you do not have any preference installed, your configuration is completely kind of like intact from that viewpoint, then if you remember the decision process is that if the preference is the same, you prefer the route with the shorter AS pass length, okay? So if it so happens that your provider advertises you a route with an AS pass of length 1, and your customer advertises you a route with length 2, you will prefer the provider route, okay? So that's why you configure a preference in the first place, is to make sure that you do not prefer based on the AS pass lengths. And so it makes sense that the counterexample should be this one. So that's kind of like, that's what I was saying. So when you see this, right, this is what you see as the output of the counter of the verifier. Then you need to figure out, okay, what is the problem? Well, okay, my selection policies are essentially missing. Okay, so you need to do this gap, bridge this gap, which is to figure out what is it that you need to change in your configuration, your selection policies, in order to fix that up. And that is arguably hard as well. Okay, so it's easy in this example, of course, but much more complicated in real life. So synthesis will bridge this gap automatically, but that will be for later. So really now it's all about how do we find this counterexample, okay? How can we efficiently and automatically produce this as the output, okay? That's what we look at in the rest of the day. And the key idea that we'll explore together is essentially to represent the network as a very large Boolean formula, so logical formula, that captures essentially the semantic of the network. And that means that can relay the output of the network to the input. So in a nutshell, what many verifiers do today is they take the topology, the configuration, the routing inputs, and the spec, the specification, build this gigantic formula according to the semantic of BGP, give that to a solver, and then ask the solver to find values to these variables such that the specification is violated. And if that's the case, then you get the counterexample. And if that's not the case, if it is not possible to find values to the variables, then you're fine. Then it means that your network is correct. So there will be a lot of mechanics involved in order to essentially capture and transform a network into a big, gigantic formula. So equations, you can think of it as equations as well. So that's really at a high level how it works. So we will model the network symbolically as a combinatorial circuit. So this is very commonly done in hardware, where you model the behavior of a chip with a SAT solver, for instance. So we'll do the same, but now we'll use, of course, like a BGP network. We'll represent that. We'll encode the input and the output and the semantic of the routing protocols in this formula as well. So we'll essentially constrain these variables so that they can only take values that make sense from a BGP viewpoint. Okay, so we'll have to capture the logic of the protocol through formulas. And then we'll give that to a solver, a theorem prover, if you wish, and then we'll ask the theorem prover to find values so that the entire formula is true. So we'll ask the solver to find assignments that are compatible with the constraints so that the entire formula is true, if possible. That's really kind of like, again, like how many verification technologies work nowadays. So in order to do that, we'll use, as I said, like a solver, an automatic theorem prover for verification. So the really very popular one these days is Z3. Perhaps some of you have used it already. It comes from Microsoft Research. And Z3 is actually not a SAT solver. It's a solver for satisfiability modulo theories, SMT. But you can really think of that as a kind of like generalized SAT solving. So it's kind of like a logical formula where you can have more complex operations than just and or not, etc., or implications. So you can have like different theories, hence the name, satisfiability modulo theories, where you can, for instance, reason about arithmetic, for instance. So there are like different extra theories that you can add that SMT then is able to find assignment for. And we'll use a few of these theories also here in the context of networks. So the SMT solver takes as input a set of logical constraints and then returns you concrete assignments for this variable as an output or unsat. if there is no such assignment. So these are the kind of like the two possible outputs. Of course, it can take a while for the SMT solver to return this. So they are solving a very hard problem in the back. But the reason why so many people are looking at SMT solver now as a powerhouse to solve this verification question is that there has been tremendous progress in SMT solving technologies. So these SMT solvers now are really kind of like industrial grade, and they can really solve immense problems, actually very, very fast. So it's still cannot solve undecidable problems, of course, but their heuristic are very efficient nowadays. And it actually works well in network verification. All right, so still 5 minutes. So this is just an example of a very basic SMT formulas that, in this case, just support constraint in first order logic. So you define a solver, you define here an integer x, and then you define some constraint. So x should be smaller than 5 and greater than 3. And then you can essentially ask the solver to figure out like what values make this entire formula true. And of course here it's x equals to 4. So we'll use SMT, or you will use SMT also during the practical exercises, but essentially SMT supports all kinds of comparison operation, so arithmetic comparison, if and only if, computations, of course negations, implications, if, etc. So it's actually quite powerful and very, very commonly used. So if you only take one thing from this lecture, if you don't care about the network verification, is that you should really check out SMT because it's a very popular and powerful tool for solving all kinds of problems, really. So it might unlock whatever problem you are trying to solve. Yeah. Yeah. So you can think of the SMT solver as a kind of like generalized SAT solver. So SAT solver is really just, you have like a Boolean formula, right? And then you try to assign values to the Boolean formula so that the entire formula is true. And the set of operations you can have is very limited. So it's and, or, for all, exist, etc. And so with SMT, it's kind of like a generalization of that, where you can, for instance, have integers as variables, and you can have like greater than, less than, etc. as constraints. So this is one example of theories where you will have essentially arithmetic constraints that you can have. You cannot have this in a SAT solver. What an SMT solver will do is that they will take this, they will translate that into a SAT formula, and then they will essentially call a SAT solver internally. So you can think of it as a kind of like more abstract solver that then turns the formula into a SAT formula, roughly. Yeah.
Can you use floating point variables as well?
Yeah, there are theories that support that as well, yes. Of course, you will pay the price. I mean, the more complex the theory, you can also start combining the theories together, but the more theories you use, the more complex the theory, the less efficient the SAT solver will, the SMT solver will become. There are really, for this, we only use very limited, in our context, set of theories. I mean, the less, the better for efficiency. But you can check on the Z3 webpage. There are like tons of theories that you can use, and there are always new ones that are being developed by the theory community. And I'm sure there are experts here in the room who can explain all the set of theories that exist and the new ones that are coming up. But it's very, widely developed and very popular. So, yeah. Other questions? All right, okay. So just to finish before the break. So essentially right now I haven't done anything, right? But I'm telling you we'll try to use an SMT solver to solve that problem. So that means we will replace this verification box with Z3 and SMT solver, and then we want this box to return true. The network is correct or a counterexample. So that means we'll have to turn the topology, the configuration, the specification, and the environments, all of that into a gigantic logical formula. So that will be what we'll do after the break, is that we'll start to do this. We'll start to see how we can capture the logic of these 4 blocks into logical formulas, and then we'll see how then we can give that to Z3. So for this, we'll encode the topology and the configuration in a symbolic network model that captures the semantic of the protocol. We'll, of course, encode the specification as a formula as well, as constraint on the state that the network can have. And then, of course, the environments will be simply constraints on the inputs as well. All right, and I propose I do the break here, just because I don't think it makes sense for me to start this for 2 minutes. So let's have the break here, and then we resume at 10:30, I guess.
Yeah. So can I ask?
That means that we'll try, or we'll have to describe the topology, the configuration, the specification, and the environment as a logical formula, and then give that to the solver. And then at the end, we should get a counterexample, or true if the specification is valid. So as I said, we'll also do some practical exercise a bit later during this session, but the idea is that, for instance, you can run it. So we'll actually run the exact same example as the one here on the slide, where we should prefer the customer over the provider. And then if we look at the code, which is not here. So this is the specification that this verifier is currently verifying. So this part doesn't really matter. This is the part that matters. So essentially, what the verifier is verifying is that when there is a customer route which is available, then it means that everyone, so A, B, C, and D, select these routes, okay? So in the topology, C is the router which is connected to the customer, as you can see. So here, the specification is just saying that when there is a customer route available, then we want C to select the customer route, and then we want everyone else, A, B, and D, to select C. If you remember in BGP, the internal routers, they select the egress, then the egress, of course, select the external neighbor. So this is exactly what it means. And so here, we have this verifier, which we built for our lecture, which is essentially taking the topology as an input. So we define the topology here. We had a bunch of routers, A, B, C, D, two external peer, a customer and a provider. We define the links with the weights on the links. So we also assume shortest path routing internally with these given weights. We define the BGP sessions, the IBGP sessions and the eBGP sessions. We add them to the network object. We define the specification, which is the one I've showed you here, over there. And then we essentially create a solver, which is a Z3-based solver. And then we add all these equations, so these constraints that I was talking to you about. So here, this is what I will explain you is how do we write these equations automatically from this network object. These equations will capture the semantic of the protocol. And then we add the specification to this formula, and I will explain in a second why we do the nut of the specification and not just the end of the specification. There is a reason to that. And then we kind of like done. We can then ask Z3, the solver, to check whether this formula is satisfiable or not. And since I'm doing the nut of the specification, if the formula is satisfiable, that means that I have a problem. So I have a counterexample. Then I'm returning that the specification is violated. And then I'm getting the counterexample by essentially asking for the assignments to these variables that make the formula true. And then I just print that. Otherwise, the specification is satisfied. And as you can see here, I do get an example of, my counterexample is the following one. So it's kind of like the same that I was describing just before the break. As you can see here, what I'm learning, there is no preference set in this network. There is no selection done. So everything is based on the S-path length, effectively, because of that. So as you can see here, the verifier is returning that the network is incorrect because I can receive a pass on the customer with an AS pass of length 2 and a pass on the provider, a route on the provider with an AS pass of length 1. And that means that if I have this, then the provider route will be preferred. And the provider route in this case is learn at router B, as you can see here. And then this is what this counterexample tells me. Like B will take the external provider route, and then everyone else, A, C, and D, also take as next stop B. Okay? So this is incorrect. So that's exactly a counterexample that I can see. This is a concrete set of input routes that violate the specification that says that customer routes should always be preferred. Okay? So as an operator, then you look at this and then you realize, okay, I've forgotten to configure my selection policies. And then I can, of course, do that. And then we'll see how to do this later. And you will be able to play a little bit with the verifier as well. So I hope this is kind of like also demystifying a little bit these things. But effectively, this is what we'll do now in a second. And then perhaps what I can show you just before also going in there is that you can, of course, run the verifier like this. And for instance, you will see that I have many equations. So these are all these equations that are capturing, as I said, like the semantic of my network, the selection process of BGP, etc. So all these equations are what we are going to see now. Is where they are coming from, what they model, and so why do they work at all? Okay. All right. So I hope things are clear for now. So let's get into it. So the idea again is to model everything symbolically, and then we want to check that the specification holds all the time. Okay. So in all possible environments. Okay. So one way to do that would be to give to the SMT solver all these constraints that capture BGP semantic, the specification, and then the environment, do a big AND between them, and then give that to the solver, and then hope that the solver gives us the right answer. As I told you, this is not correct. There is a reason why I did the not of the specification, is that if I give that to an SMT solver, the SMT solver would just return to me like an environment in which the specification is verified, but that doesn't mean that the specification is verified for all the possible environment. Okay? So if I do that, I might effectively just get, okay, this is an example of two routes where the customer is preferred because the ES path length is smaller than the provider, but it doesn't tell you that if the ES path length changes, then the customer will always be preferred. So what you need to do really is to give the not of the specification and then ask the solver to find an assignment where the opposite of the negation of the specification is valid. So that means that if this is satisfiable, there is at least one environment in which the specification is violated. So that's clearly a counterexample. And if the formula is not satisfiable, then it means that for all the possible environment, there is no environment that can make the specification untrue. Okay? So that's why we negate the specification in network verification. So it's just like to make sure that when it is not satisfiable, we can get a guarantee that all the environments are safe for us. So it's a small trick, but it's just like it is an important one. Otherwise, the results don't make sense. Okay, so effectively, we start from here. We need to model everything symbolically. And that we need to do that because the SMT solver, of course, does not know BGP at all. So that thing really just get the formula in, find variables find assignments to the variable, and then that's it. All right, okay. So the first thing that you need to model are the inputs to your network, okay? So the inputs to your network, the routing inputs to your network, you need to kind of like model them with logical variables. And so here, we have like a simple network with two external networks, one provider and one customer. And so we define like some Boolean variables that are like attached to that. As you can see, we have like one variable for the local pref, one variable for the next stop, one variable for the ES path. And then we have a Boolean flag which is available yes or no. So these available yes, no represent the fact that a neighbor might or might not send you a route. So this is how we represent it logically. So if available is false, that means there is no route there. And if available is true, that means there is a route. And then the local pref next up and ASPath will just take some integer values. For instance, here it will be a string, an IP address, and here we represent that as a list of integers. You could also represent just the length of it if you want. So we have these variables that are attached to a route object. And there will be two route objects that come from the exterior in this topology. Okay? And of course, we generate this automatically, right? So you give me the configuration like this, and then we automatically create these routes, these symbolic routes that represent this external announcement. So this will be what enters the network from the left. Okay? These are the routing inputs. And as I said, the dot available is just a flag that indicates whether the route is there or not. So again, what we are looking at is, for the solver, the task of the solver should be to try to find assignments to these different variables, local pref, next talk, the ASPath, in order to violate the specification, okay? So that's kind of like what the solver needs to do. So there are three components in our encoding. The first one is the one pertaining to the network model. So this is where we capture constraint about the routing state, the routing semantics. We need to teach it how to speak BGP effectively. Then we need to encode the specification, and then we need to encode any constraint on the environment. These two are actually much simpler, so we spend most of the time on the symbolic model. So I've explained you how we represent basic properties about the external routes. Now we look at how we represent the routing state internally. It's also basic, so there are actually kind of like the same variables, or like type of variables that are represented there. So internally, we want to represent that the router can have a route yes, no. So this is this dot available. Each router will learn a route with a given local pref and next up, and with a given ASPath. So these are just replicated from the exterior routes attributes that are replicated here for the internal router as well. So that's kind of like same as before. So far, there is really not that much that has been made. But the issue is, of course, that we cannot just allow the solver to give values to these variables arbitrarily. It would make absolutely no sense. We need to constrain the formula so that the solver will only find values that make sense from a BGP viewpoint, okay? So this ASPath, this available local pref, etc., somehow these values here, they have to be tight and constrained to the values that are learned externally, okay? You cannot have a route coming from a provider with an ASPath 1, 2, 3, and then an internal router picking a route with an ASPath 5, 6, 7. Okay, it makes no sense. They have to be linked together. So that means we need extra constraints to do this linking in the formula. So again, like we need to constrain the values here that these variables can take with the values that these variables can take over there. Okay, so we need to add the glue essentially between the two. That's what we need to do. And we have to do that by coming up with equations, essentially, that capture the semantic there. And this is essentially what I will explain you now. So there will be two parts. So we need to essentially constrain these variables according to the propagation rules of BGP. And then we also need to constrain these variables according to the selection rules of BGP, okay? So we have to constrain the fact that neighbors exchange routes with each other, and routes don't appear out of thin air. So I need to be able to constrain the fact that if I'm selecting a route from a neighbor B, I need to have received that route from B. B must have advertised that to me in the first place. That's kind of like the first step. And then if I'm selecting the route from B, and I'm learning also a route from A, that means that B routes is better than A's route, okay? So I also need to encode the fact that there is this selection step which is made, and then routers will prefer routes from a neighbor according to the logic of BGP, preference first, ASPath length after, then tie-breaking rule. Okay, I also need to teach the SMT solver that there are these rules that BGP cares about. Okay, so I need to capture these two things. All right, so first let's look at propagation. So as I said, in propagation, we need to now work a little bit more. So we need to add a new variable here, logical variable, selects from, that represent the fact that these internal routers, they learn the route from someone else, so from another router, okay? So what we want to be able to do is to kind of like add constraints that defines what the select from can do, okay? And we also want to kind of like capture the semantic of the fact that in order for a router to have a route available, it must select the route from someone. Okay? These routes, that again, they don't appear magically out of thin air. So the select from is just a variable that can be the ID of a neighbor. So it can be, if you are D, for instance, A, B, C, or D itself. Or it can be just invalid, garbage, something else. Okay? So yeah, questions? In this particular example, it's the same. That's a good question. In more complex network, it's not necessarily the case. So in more complex network, you can have a next stop, which is different than the select from, because you can have kind of like relays that are like redistributing routes on behalf of other routers. So you do that in order to build a hierarchy. So if you think about a network like Deutsche Telekom, they can have thousands of routers. So you cannot build the full mesh of BGP sessions between all the routers. It doesn't scale. So what they do is that they will have a few routers, typically in the core, that are known as reflectors. And these reflectors, they will collect the route from the exterior, and then they will redistribute that internally. So in that case, what you have is that the next stop will be one of the egress, but the select from will be one of the reflector. So this is just a model that allows to model this, this distinction. In that particular example, it's so simple, we could just avoid it. But since this encoding also supports reflection, that's why it's there. But that's a good question, yeah. Yeah, okay, thanks. So select from just represent here the ID of a neighbor or invalid if you haven't learned the route at all. So that's kind of like the first constraint we have in our model. We'd simply say that in order for a router to have a route available, in order for A to have a route available, we say that, so this equal actually means if and only if in Z3 terminology. So we say that A has a route available if and only if A selects a route from a neighbor, okay? So this is an if and only if. And that A selects a route from a neighbor, it's actually an OR of three things. So A will select a route from a neighbor, either if A, the select from is equal to B, C, or D, okay? That looks trivial, but you still need to teach trivial things to the SMT solver in order for it to understand the semantic of routing in the first place. So that means that whenever route.available is true, selects from must be either B, C, or D, okay? And whether this part here is anything else than B, C, or D, then you want this to be false. You want the if and only if semantic to be respected here, okay? So again, like this is just constraining, if you want, the fact that route available, this value can be true only if you select the route from a neighbor. So it's kind of like connecting the dot available with select from, okay? And like restricting the values that select from can take. Again, if you don't do this kind of thing, you can have a select from that can be 1,000, for instance, even though the values are only 1, 2, 3, 4, for instance. So you need to restrict, of course, the select from to be only one of the ID of your neighbors. So what we do, of course, we do this in a programmatic fashion. So you will see the code, the Python code is essentially iterating over all the routers in the network and then creating these constraints automatically, okay? So you don't write this manually, of course, you generate that automatically. And so what we do, we iterate over all the routers and then over all the neighbors of each router, then we create this big OR, okay? So this is kind of like how we end up with a lot of equations, but they are just generating from basic principles very easily. So that's the very first step, and right now I haven't done much things, but the only thing I've done is connect this variable .available with this variable selects from. That's kind of like the only thing I've done, but this is already required in order for the assignments to make sense, so that we don't start to have like routes that are routers with route available while they don't learn them from anyone else. Okay, that's kind of like the first step. That's kind of like, as I said, like the first steps. So now I need to really encode the propagation logic, okay? So I want to prevent the solver from like taking shortcuts. And that's, if you're not careful with how you encode, the solver will find shortcuts. That makes no sense from routing viewpoints. So right now I've connected, let's say, this variable here with this variable there. what I want to ensure now is that if RA that selects from, let's say, is B, I want to make sure that B actually send a route to A, right? And not just that A is saying, I'm selecting from B while B didn't send anything to A, okay? So we need to constrain not only on a per node level, but now we also need to constrain on a per network level. We need to start to put the variables here we need to start to constrain them with the variables over there and vice versa, okay? So we need now to look at the propagation across the network. So now we start to look across more than one router. And so this second equation is actually saying this. So we say that RA will select from a neighbor if RA really receives a route, okay? It's not just that RA can create a route, it has to receive it. And so here, in the case of A, from the topology, as you can see, A can receive a route either from B, C, or D. So this is kind of like what is represented here. And so what does it mean to receive a route in BGP? So if you think now we are in concrete BGP, so this is why the colors of the slides have changed. So if you think about what happens in BGP, when you receive a route from a neighbor, you kind of like transform the attributes of the routes that this neighbor is sending to you, or at least you may transform it for some cases. So for instance, if you have a route that is advertised by B, so the route, of course, will be available on B. Let's say it has some local pref, it comes from this next up provider, and has some AS pass. Then what you have on A is that A, depending on the logic, might have that route available or not. So here, there is this notion of filtering that routers can have in which they can drop routes if they want to. So this is why the fact that the route is available here does not necessarily mean that the route is available there. So we need to be able to reason about dropping of routes. We won't do that in this session, but technically that can happen. The local pref can be modified as well. So it's not because you have a local pref of 100 here that you have a local pref of 100 there. So we need to be able to model transformation of that value to something else, these values to something else. The next stop will remain the same. So if the next stop was here, the next stop will be set to the routers that advertise you the route. So here, if B advertises you a route, the next stop will be set to B, and then the AS pass will be unchanged. So all this to say that when a route propagates in a network, a BGP network, some values of the attributes might change. Some values will be set to fixed values. So for instance, here the next stop will be set to the ID of the router advertising all the time. And then some values like the AS pass will be untouched. Okay? So this is just like we need to be able to encode that through constraint as well. So some values untouched, some values fixed to fixed values, and then some values possibly transformed. And so here we have we do that using symbolic expression. So we have like a function, if you wish, that is transforming routes that routers propagate to one another. And as you can see here, the routes that A will have will be the transform routes that B is advertising. And so these transform routes, it will be some expression that will be applied on the different attributes. So for instance, the available and the local pref might be changed, as I said, so there will be an expression that captures these changes. The next stop is fixed to the originator, so this will be always be set to B when B advertised a route, to C when C advertised a route, to D when D advertised a route, etc. And the AS pass will also be untouched. So this is kind of like a transform route, and if you look in the code, this is really what is happening here. Semantics. So we have a transform route function, which essentially represent the transformations that a route going from a source to a destination will undergo. So these objects, you can call it, and then it will apply essentially these transformations to the route. So all this to say that this is kind of like encoding the fact that the route is moving from one node to another, and then its attribute is changing according to the logic of BGP. That's what this function is doing, nothing more. So coming back to this equation, we say that RA selects a route from a neighbor if and only if it receives a route from its neighbor. And this is an OR with essentially the routes coming from any possible neighbors that you may have. So A here has B, C, and D. So you transform the route from B, transform the route from C, transform the route from D. And that encodes the propagation logic. Simple propagation logic, but still propagation logic of BGP. And of course, again, we do that automatically. You don't do that manually. It makes no sense. So we have like a for loop in which we iterate through all the routers, and then we generate all these equations accordingly, depending on all their neighbors. So effectively now what we have, not only have we connected, constrained dot available with dot select from on this router, we also now have constrained dot available and dot select from across the different routers together. Okay? We have also now taken account of the propagation between different routers. So now we are making progress in capturing the semantic. We still haven't really constrained these values there. This local pref, next stop, and AS pass, we also need to constrain that. Otherwise, again, the solver will pick arbitrary garbage values if we don't tell it to take some specific values instead. So we still need to do that. So this is this part now. Now, this constraint, these other new equations, what it's saying is that if A is pinging a route from B, so if the select from of A is B, so that means that A has selected the route of B, then what it means, what it implies is that, well, first, B has advertised the route to A, and then the attributes of the route that A has are the same as the transform route that B has sent, okay? And so that means that the local pref of A will be the transform route local pref, that B advertises, the next stop that A uses will be the next stop that of the transform route that B advertises, et cetera, et cetera. So here, the only thing I'm saying is that the attributes of the route that A selects are linked directly to the attributes of the route that B advertises, okay? They don't come, again, out of thin air. They must be equal, okay? If A selects the route from B, and the local pref of the route of B is 200, then the local pref at A must be 200 as well. It cannot be 150. It has to be 200 exactly, okay? Same thing with the next stop. If the next stop is B in this case, it must stay B, etc. Okay? So now we are constraining, again, these values so that they don't get out of hands and they stay within the BGP semantic. So this is what these equations now are meaning. And that effectively now allows us to have constraints on the other variables as well. So as you can see now, we have constraints on available, select from, and all the other values as well. So now we are like making further progress in like capturing the semantic of BGP. So that is already a lot, I realize, but this captures essentially the propagation, okay? So how route moves and how attributes are kept or changed as the route moves inside the network according to your configuration. We still need to capture one more thing, and then we are almost done. It's the selection. So we need to tell the solver that routers prefer routes with a higher local pref, they prefer routes with shorter AS pass length, and then there is a tie break as the last step. So we need, of course, to also have constraints for this. And this is actually not hard at all to capture. So, so this is one equation that actually does that. So what this equation says, it's not too hard, but it says that if RA does not select the route from RB, so if the selects from of RA is not RB, but RB advertises a route to RA, so the transform route is available over there. So that means B advertises a route to A, but A does not pick it. So this is possible, but that implies that the route that A has is preferred over the route that B has advertised, okay? So this is what this part means. So it's okay for B to advertise a route to A and A not to pick it, but then A must have a better route. Otherwise, it makes no sense from BGP viewpoint. What does it mean for A to have a better route? Well, it means that the local pref of the route that A has is greater than the local pref that B advertises. That's one reason that A may have a better route via another neighbor, another next step, sorry. Or if the local pref is the same as the local pref of B, it could be that the AS pass length that A knows is shorter than the AS pass length that B advertises. That would be the second step in the decision process. Or you have the same local pref, you have the same AS path length, but then you have the other tie-breaking criteria that are different. So this is just like encoding the BGP selection process as we have seen together. As I said, in this lecture, we really only care about local pref and AS path length, so only the first two parts here. But the BGP decision process is much more complex, as I said as well. And so you can put that together. You can essentially kind of like take this equation we have just seen together, and you can also encode the fact that so you can essentially capture this through an if statement. So if A selects from B, then it means that, so if A selects from B, then it means what? It means that the route is available and A picks the route from B, or A picks another route than the route from B, and that means that the attributes of A are better than the attributes that B advertise. So it's essentially picking the two equations that we have put together and just making them combine in the if statement. That's it. And of course, again, we do this programmatically. We iterate through all the BGP sessions, and then we generate this constraint from there on. That's it. So these are like, again, like not easy equations to get, I understand that, but these are not too many, and these essentially capture the basics of the propagation and the selection of BGP. And this, while it doesn't capture all the complexity of BGP, it captures kind of like an interesting subset nonetheless. So with these simple rules, you can already kind of like verify practical network. Okay, then the specification, I already showed you one, but essentially the specification is extra constraint, extra equations on the routing state that you want to see or not see in your network. So for instance, I already showed you how you can, for instance, indicate that you always want the route from a customer to be picked. Perhaps you want to prevent this case over there, that you don't want to transit routes between two providers. So here you could say, for instance, whenever I pick a route from a provider, I should never advertise that route to another provider, right? You can capture this as a logical formula. You can check that every route is tagged or whatever. So you have many properties that you can just write on your routing inputs and the resulting decisions that your routers are making. You could also verify forwarding states, etc. We won't do that in this lecture, but you can essentially do a lot. So for instance, I've showed you already. So if you want to verify this network here and the fact that it should always prefer the customer routes, so the way to do that is to say that whenever there is a customer route available, so whenever customer.route available is true, then you want all the routers inside the network to select it, okay? So you want the C routers to select the customer route and then all the others to select C, okay? That's essentially how you can capture that property over there. So that's it for the spec, not complicated, and the environments constraint, they just, of course, constrain what you can receive from your neighbors, and most of the time, you actually don't have any constraint there. You just allow anything to happen from the exterior. So here, typically, there is nothing. You just allow everything. So there is no extra constraint that are being added there. So again, this SMT-based encoding, it's actually inspired from the encoding that one verifier uses, Minesweeper. So this is a SICOM paper in 2017. So there's been a lot of work on essentially verifying different types of protocols, with different tricks, different specification as well. Using SMT, so Backpipe, Minesweeper, and NV, like published at very different conferences, as you can see. So UPSLA, SICOM, PLDI, so more PL conferences and more networking conferences. So these are all based on SMT. So essentially, if you read these papers, you will see equations that are like very similar to the ones I've presented today. And then you have been also, there's been a lot of papers about, of course, making this verification more efficient. So I mean, this goes without saying that if you were to try to verify a huge network like DT sizes with this approach, this SMT-based approach, you will end up with equations that are humongous. And so at some point, of course, even if SMT solvers like Z3 are efficient, they will start to struggle, and then it might take a very long time or never terminates. So there's been also a lot of work about improving the scalability of the verification using different techniques. So Kirigami, as the name indicates, for instance, tries to cut the formula so that it becomes smaller, and then it's more amenable to a verification by Z3. And Lightyear, I think, if I remember correctly, what they do is that they go hierarchical. They try to go divide and conquer, and then to verify the networks in layers. So first a high-level layer, and then they try to decompose the verification into sub-modules. So they try to verify some properties at the network-wide level, and then some properties at, let's say, a local level. And then combine this so that it still works. So it's kind of like a hierarchical verification approach there. And you see a lot. I mean, there's a lot of research there, effectively. We also work on verification, of course. So this is just a few examples of work we have been doing in the area. So this paper in SICOM 20, where we looked at probabilistic properties. So here we extended the type of properties that one can consider. And we were interested in properties that are not necessarily black and white. You know, like, for instance, if you think about load balancing. So let's say that you would like your network to load balance the traffic. So this is an example of a property that you want there most of the time, but it's okay if it is not there all the time. You know, if there are like link failures, many link failures, it's okay that load balancing property is violated for a little while. So there is a lot of, in many practical situations, you have like service level agreements where some operators, they want the property to be true in 99.999% of the case, for instance. So that means that you cannot use verification for those in the sense of what I've shown you, because there are counterexamples that violate this property. It's normal. What you care about is how many are there. Are there more counterexamples that the property of them being seen in the network is more than 99.999 or 0.0001%, for instance. And so it's a harder problem now, because not only do you need to be able to compute counterexamples, you also need to count how many counterexamples there are, okay? So now you need to do what is known as model counting. You need to count how many solutions there are to a satisfiability question, not only find a concrete set of assignments. So that, of course, makes it even less scalable. And so in this paper, what we did is that we had like techniques in order to figure out, we were looking at failures, link failures, which link failures can affect the property or not. And so by doing this, we're able to prune actually a lot of failures that we know for sure will never affect the property that you care about. So if you think about, for instance, shortest path routing, any link failures which is outside of a shortest path tree will not affect the shortest path tree in this case. So you can already prune all of them if what you care about is whether your shortest path tree would start changing after failures, you know? So it's just one example of an insight of like pruning that you can do in a property guided way. So that's kind of like what this paper was doing. And then perhaps just the last one before we go to the practical side of things. But this is another papers that we published 1 year later, where we realized, of course, that and it's great to verify networks, but what if your verifier is incorrect? You know, like, and it's these equations. I mean, they are hard to get right. So you can make mistakes in your equations, meaning that you won't capture the semantic of the network anymore. And that means then that you might actually start to generate false positive and false negatives. So your analysis now starts to be out of sync with respect to what is happening really in the network. And it so turned out that we took here a bunch of state-of-the-art verifiers, and then we looked for mistakes in them, and we found many bugs, which is not that surprising, inside the verifiers. So essentially, the verifiers were saying that some networks were correct when they were not, or they were saying that some correct networks were incorrect while they were correct in the first place. So both cases of false positive, false negatives, we found example. And so, of course, this is why it's called meta, right? So now we are trying to verify the verifiers, and so you can see that this can escalate. So at some point, of course, you have to trust that you have captured the semantic right. But so these tools, and it was a testing tool, so we discussed about fuzzing there. So we effectively here we fuzz the verifier with input configuration and input environments. And then we also had kind of like a virtualized network that we could also run this input in. And then we were comparing the output of the verifier with the output of the real network. And then whenever there was a discrepancy between the two, we knew that the verifier was incorrect because it was not predicting the output correctly. And of course, you want to be smart in what kind of inputs you need to exert the verifiers with in order to kind of get some coverage. So that was this work.
Did you do this in response to the Facebook problem here, or in anticipation of their name change to Meta? Because
no, but there is an H there. I think in men.
Just not to be in trouble with the naming police.
No. I don't think Meta. I mean, I think the Greeks were first in inviting it, probably.
If you put something like today, Meta, it sucks or something.
Yes. But fair enough. But we didn't have any complaints coming from Facebook on that. So the fact that the H was there is because we were referring to the meta-analysis there. Yes. All right. Then, if there are no more questions, I think what I would propose you to do is to essentially play a little bit with the verifier yourself and then get the feeling for how it works. We have 40-ish minutes, if I understand correctly. So it will be relatively quick and high level, right? We won't have the time to go into the details, but still, I just want you to actually see that these things are actually easy to run and quite amenable. So I think here, so what I need to do is send a URL to everyone. How can I do this?
Maybe you can generate a QR code.
Yeah, exactly, yes. So
Generating a QR code is probably the easiest, and then rely on everybody's devices.
I don't want to sign up though.
Oh, here we go. Let's see.
Okay. All right. So you can try to scan it. Does it work?
Well, it's a sign-in link for GitLab.
Oh shit. That's so it's not open.
It's not as open.
Okay, that's all right. So I will create a public repo on GitHub then.
So maybe just a list, because we can see all the projects in the groups.
You what?
I can see all the projects in the groups.
Ah, right. Okay. Oh no, sorry. I know why. Tac. All right. Okay. So that's the reason. Public. Save. Can you try again? So normally the repo now is public. So does it work? All right. Okay. Good. Yes. Sorry. Here. All right. Okay. So clone the GitHub the GitLab the Git repo, and once you have done that, you will see that there are some instructions to install Z3. So if you happen to have a Mac or a Linux laptop, then it's really a one-liner. I didn't have a Windows laptop to try it with, So if you are running on Windows, we have about 30 VMs that are running at ETH that are running on Linux. So if you need to access those, you can, I will write down the URL, and then I will give you the port and the password. So, how many people would need access to a VM? One? Just one? Everyone else has a Linux or Mac? Okay, good. So then I will just write to the URL there. So you will see on the Git repo there is a README already with the instruction to install Z3. So this you can do right away. So normally it's a one-liner, and hopefully it works. And then in 2 minutes I will go through the assignment with you, and then we'll explore that together. So I will just get you the URL of the VM right now. All right, so for those of you who need a VM, I think there was at least one. You can just connect yourself to one of those and then start working there. So you had one, right? So we have let's say you take the... Oh, right, okay. But so just if someone takes a VM, just say so that we don't over... we have one person per VM.
Question.
Yeah.
Maybe that shows my ignorance from before. Are the network topologies, the links, are they directed?
They are indeed, yes.
Because
so they are.
It says here A to B, but not B to A or something.
Yeah. So I think.
Yes, that fine.
Yes. So so it could be that the encoding here assumes bidirectional links, but there's nothing in the.
So this could mean that it's both directions.
Correct, yes. So when you add a link, you add a link in both directions. But
yeah, otherwise I was not seeing how to get from B to A.
Correct, yes. So it's a syntactic sugar.
Yes, yeah, but
but an important one, I agree, yes. All right, so I'm assuming that, you can install the Z3 again, and that things are running locally. If not, connect yourself to a VM and then do it from there. So as you can see, what we'll do is just explore a little bit the verifier together. So there are a few files here that you can find in the repo. There is the verification.py, that's the main file in which we define the topology. And then you have a bunch of other files, like routing semantics is where all the equations are defined. So you can see in routing semantics, these were essentially, I'm running these for loops that are creating these equations. This is like the steady state equations, so the equations that describe the state of the network after convergence, and this is the propagation equations. So you can check that file for seeing a little bit of these equations are put together. So that's the routing semantic. Routing state is describing what is a route. So it's basically in helper function what is a router, etc. So you won't need it, but it's just defined there in case. In task.py, you have example of specification that are there. And then network.py is helper function for describing what a network is. Okay? So these are the various files. And so the idea initially is that you just execute verification.py, and then you look at the fact that the specification is violated. We already showed that together. And you can look at the concrete examples and reason a little bit about it. Then once everyone is there, then we can actually fix the network. So by setting the preference, right? Because so far the preference is not set, that's clearly the issue. And so we'll do that in the second step. And for this, you can use this route map function, which is just a filter that sets the preference, okay? Now I'm giving you already kind of like the signature of the function that you need to use. And the only thing you need to look at is, I mean, what is a route map composed of? Is essentially a predicate that applies on the route and then an action that is executed on the route when the predicate is true. So here the predicate should be any route that I'm receiving, I should set a local pref to it, okay? That's kind of like the idea of that steps. So it's really a one-liner that you need that sets the local pref to a higher value than the default one, which is 100. So any values higher than 100 should be. And at this point, your network should be correct, okay? So already there, if you can reach that point, there will be a specification is met or is satisfied in this case. And then after that, we'll see whether we have the time, but the idea would be for you to work with a harder specification than just this one. And the specification would be that the network should prefer customer routes all the time unless the provider advertises a route with a given community. So community is just a label. So routes can have communities, can have labels. And here, the only thing that it says is that if the label of a route is 5, then it's okay for the provider route to be preferred. Otherwise, you should prefer customer routes. And I'm giving you the skeleton here again that you can just copy paste, and then you essentially have to complete the if part over there. But we can do it step by step. Start with the easy part first, and then we'll see whether we reach that part or not. Yeah. Yes, yes, it is.
I was about to draw a graph now. We see the graph.
Yeah, sure, yes. But was that your question? Ah, right, okay.
Because these things are hard to get to draw the graph.
Yes, you're right, you're right.
There's ABCD and provider, there's also customer. Ah, this is the one, yes, we say. ABCD.
Ah.
Okay.
Okay, it doesn't like the...
But that's from B to A.
So I think it should be this one, if I'm not mistaken. What you also have are weights that are not depicted on the slide. But the weights are not important for these questions. Is it correct?
Provider, C to customer.
Yeah. So this is the network. It's true I could... It's what?
It's fully connected. In a sense, isn't it? I mean, the graph is connected.
Yeah, and you have a full mesh, I think, of BGP sessions as well.
Ah, maybe they go around.
So does everyone manage to run it at least and get the violations over there?
I see this, yeah.
All right, good. So here, this is the violation that we saw together, right? So this is an example in which the customer receives an AS path length which is longer, 2, than the provider. So it makes sense that this is the route which is picked. Now, if you want to make this slightly more interesting, but still incorrect, we can add a constraint in route semantics that forces the AS path length to be equal to 2, for instance, on all the external routes. So now, essentially, what I'm telling the solver is that I'm forcing it to have examples where the AS path length for the provider and the customer will be equivalent to each other. But it will not make the network correct, as you will see. So, clear.
So can I put back
Yeah, just 1 second, and then just for people to understand there. So now I've put an extra equation that forced the external route to have an AS path length of 2. But you can see that the solver still managed now to find a counterexample where the provider route is also picked. So what is going on here is that, as you can see, like now B is picking the provider, so this is already violating. Then we have C, which, A is picking B as well. So A picks B, B picks the provider, and then the 2 others picks the customer. Why is that the case? Now we have to dive a little bit deeper in this topology. So now we receive 2 routes with AS path length 2 here and there. So B and C, they pick these routes, the external routes. And then, as you can see, we have some of the routers that pick B and others that pick C. Why? This is where we have the shortest path entering into the picture. So this is not represented on the slide, but if you look in the verification.py file, you will see that, for instance, the link between B and D has a cost of 3. The link between C and D has a cost of 2. So D is closer to C than it is from B. So because of that, D will prefer the customer routes over the routes coming from B. And so essentially what we're going now is that we are diving a little bit deeper into the decision process of BGP. And now the decision is not based on the AS path length, but it's based on the cost to reach the egress, which is there. So it's kind of like just showing you like the network is not just incorrect because the AS path length can be greater. Even when the AS path lengths are equivalent, you can still have an incorrect network. And this is just a counterexample that shows that. So we really need to set the preference. That's how we fix this issue, okay?
So the preference is the third argument to the add link?
Yeah, so what you need to do for setting the preference, essentially you want to add here a new line which looks like this, which essentially set a route map. A route map is just a filter that applies on incoming routes. And you want to set these route maps on the customer session that the customer has towards C. And then you want to complete essentially the content of this parenthesis with the logic of the filter. And essentially the filter, what it needs to do is to match on all the routes and set the preference to a high value. So knowing that the default pref is 100, you want to make sure that the preference for the customer route is strictly greater than 100. So essentially here you are adding this filter on C and customer, on the session between C and customer, and you want here to set the predicate, which should match on everything, and then set the preference value to something greater than 100. So if you want to, so for this, I advise you to look at the route map class. There is the description of the interface of route maps, and then it tells you exactly the route map items, what are the parameters there. So yeah, if I tell you more, then I'm giving you the answer. But effectively, there are 4 arguments that you need. And so read this part here, and then based on this part, you should understand what are the 4 arguments in this specific context. And again, what you want is a route map that match on everything allow, and then set local pref to a value, and this value should be strictly greater than 100. And if you do that, then essentially you are making customer routes preferred, and then the network should become correct. Yeah. And the way to check whether your network is correct, you rerun verification.py, and then you see. Either you get the counterexample, or it will tell you the specification is met, right? That's how you fix it. So that should work. We'll verify it together, of course. But so these, like the semantic of these route maps, right? These again are filters, route filters. They have like a predicate, the conditions that triggers them or not. And then they can allow a route or drop a route, and then they can modify the attributes as well. So as you can see, the first parameter is allow, whether the item allows or not. So of course we want it to allow, so it should be true. The condition here, we want it to be none because we want to match all the routes. So that's kind of like the star. All the customer routes, we want to accept them, and we want to increase the local pref. The third attribute is the local pref. I told you that by default in this verifier, local pref are set to 100. So in order to make the customer routes prefer, you should make that value strictly greater than 100. And then the last parameter is the community. Things of these are labels that you can attach to routes. Here we don't care about them, so we just set that to none. So now we can test this thing again. We can go back here, and we can run the verifier again. As you can see, the specification now is satisfied. So your network now is correct, okay? So an alternative way to do that would have been, and that would have been perfectly fine as well, is that instead of increasing the preference on the customer routes, you could decrease the preference on the provider route. So an alternative way would have been here on B, which is connected to the provider. I could have set the local pref to, let's say, 99, and that, if I'm not mistaken, should be also correct, as you can see, okay? So now you can choose one or the other. Typically, it's more logical. Operators will increase the preference where they want the traffic to go instead of decreasing the preference where they want the traffic not to go. So it's kind of like equivalent, but I think this way is seen more often. So I hope that you understand what is going on again, right? So we are looking now what we are doing is essentially increase the preference on these routes that come from that session. And so now the network is actually preferring customer routes all the time, okay? So now we can move on. Now it's a bit harder, but I think it's also more interesting. But now we want you not to use a dictionary, but to play with a slightly harder specification now. So this is a very simple spec. It was just to get you started. But of course, in practice, specifications are more complex. And so the idea would be that you try now to first write the specification that says that you should prefer customer routes unless you learn a route on the provider session that has a community 5. Then you should prefer the provider route. So that's what this specification is saying. So the way to do that is essentially you have to write this function over there, and you have to replace the specification, which is now here. So right now the spec is I want to prefer customer route, right? So if you want here, this is the spec again. If a customer route is available, you prefer it. So we don't want this spec anymore, so we delete this line, and then we replace it with a more fancy spec. So this is what you have now to complete, is to write the specification that says that you should prefer customer routes unless there is this community set on the provider route. So you should do that first, write the spec, then try to verify it. The network should be incorrect again because we haven't like done any of the logic. But first you write the specification. It's easier that way. And then after, of course, you can make the network correct again by adding a route maps that will do the right thing. So for instance, you can use a filter that will set a high local pref to the customer routes, and then another filter that will set an even higher local pref to the provider route when the community is 5. And if you write these two route maps, then the network should be correct again. Okay? So it's again a case of first writing the spec, verifying that the spec is not met, then writing the configuration, and then you should be, again, contemplating a new network, a correct network. The specification will be more complex, so you have to think a bit now. And there is a hint, right, over there, that you really need to think about all the cases in your specification. So especially, for instance, you need to think that it can happen that the customer advertises a route but not the provider. Okay? So it could be that there is available is force of the provider, but there is a route on the customer. So you should think about these cases as well. This is something that can happen, and your specification should cover it as well. So here you'll probably get it wrong, but then hopefully the counterexample will help you figure it out, right? So as you write your spec and you execute it, you will see some, concrete counterexamples there. It should guide you. So try it. We only have 10 minutes, perhaps you can try for 5 minutes, and then in 5 minutes I can show you the solution, and then we can go through it together quickly. And then we can just go and enjoy the break. After, in the later session, I will speak about synthesis, and I will end on synthesis. So that's for later in the afternoon. And I may be a little bit shorter than 1.5 hours, but I'm guessing this is fine, yes. All right. So I think I can give you one solution. There are more. There are different ways to write these specifications. But this is one that fulfills the spec. So as you can see, it's much bigger already, but it's actually not that complicated. So you essentially have two cases. One in which it's the same spec as before, where you prefer the customer route. And then you have the other case where you prefer the provider route. So you need to consider the two cases, essentially. So the case where you prefer the provider route, it's when you have a provider route available and the community is 5, okay? Then you prefer the provider route. That means that B selects the provider route and the others are selecting B. So that's one possibility where you prefer the provider route. You also need to prefer the provider route if there is no customer route available. That's what the int was actually indicating. So that's this branch part, this part here. So kind of like two cases. You prefer the customer, you prefer the provider, and the provider, you have to think about when do you prefer provider, when community is 5, and when there is no customer route available. So arguably it's not trivial, but that's kind of like the idea. And then now if I, of course, run the verifier again, it shouldn't be correct. And then you have a counterexample that violates the spec. So of course now the issue is that we don't have these route maps, okay? So we need now to add the route maps in order to implement this specification. So again, the route map, these are filters that we need to implement. So there are two filters that we need. The first one is the customer one. So the one that will apply on the customer session. This is the same as before. So you just you set a high local pref to the routes that come from the customer without any specific conditions. There we just set the local pref to 200 independently of the community value. That's the first easy one. And that is not enough, of course, because we still don't handle these community 5 cases, right, on the provider. So we also need now to set a higher local pref to the provider routes if the community is 5, and then normally then the spec will be met. So we need a second route map that will do exactly that. And this would be the route map. So this is a route map now that we apply on the provider session that matches all the routes. If the community is 5, that's essentially how you should read it, then we set the local pref to 300, and we don't modify the community further there. So now if we run again, now the verifier with this route map, yeah, it should be correct, and it is. Okay, so as you can see, we had now we have like a more fancy spec, definitely non-trivial anymore, and then we modify the configuration in order to make it met. As I hope you realize as well, I mean, people have to configure these filters, again, manually today, right? Synthesis will be the topic of the next session where we try to generate those automatically. But right now, today, people generate that manually, okay? They write them down. And it's very finicky. I mean, you have to think about the implications of setting these filters. And so that's why verifiers are, of course, very useful in that context. So it's new now, so I hope you could at least play a little bit with the verifier and get something out of it. If you so enjoy, please continue to play with it. If you want, actually, we have like an advanced lecture at ETH where we have taught verification. So the website is oh, sorry, you don't see it, it's here. So if you type in advanced topics communication networks on Google, you will find it. It's there. But essentially, we have been teaching verification and synthesis in this lecture. And if you are interested, because now you have been playing with the verification verifier, we actually have way more exercises on this than what we have been covering in 45 minutes. I mean, that was very, very quick. But you can play more. I mean, there are multiple tasks now. You already have all the setup because you installed everything. And then you have solutions for each task as well that are there. So you can really play now, continue playing and get a better feeling. And if you are so inclined, there are also exercises about synthesis, which we won't have the time to go into today. But you can also play with a synthesizer now, based on top of the verifier. So that's also would be like more advanced, but if you like this, it's already there, it's public, hopefully, should be. Yeah, so that would be a further set of resources if you are interested. So I understand we finish now, and then we reconvene at 4:30?
4:30, yes.
4:30.
And I was about to say that you have seen the cake yesterday. That will start at 4, and I think it lasts while it lasts.
Break and could enjoy some outdoors activities. So I will now talk about the second part of today's lecture, which will be about synthesis. So if you remember, we finished just before the break playing with the verifier. So you had this network, this simple network with some simple specification, and then you add essentially to configure it and change the configuration in order to make it correct. So as I hope you could realize, this is not necessarily easy to correct a network given a counterexample. And so in synthesis, the idea is not to do that anymore, but to kind of like automatically figure out the configuration. So this route map configuration that you had to do, it would be nice if you don't even have to do this. You give me the spec, and then automatically we produce the route maps, for instance. That's kind of like the idea, the dream of synthesis. So that's kind of like what I was just saying. So right now we are in this world where we have counterexample, and then we have to repair the configuration given that. So we already saw that it's not immediate to figure out how to do this. It's also something that you need to keep in mind is that you need to consider the entire specification. So oftentimes when the specification is complex, you can have a misconfiguration that requires changes in multiple places. And so it's actually easy to kind of like fix some part of the specification and break others. So having the entire specification correct is usually wrong. It's usually hard, sorry. And then we have this even more complex specification that pertains to performance that are even harder to actually fix when you're an operator. So in synthesis, what we are looking at is that the topology is an input, the specification and the environments, not the configuration anymore. And then the problem is about finding a configuration that meets the spec, okay? So it's kind of like different input outputs, but related problem, of course. So if you remember our problem this morning, we would like the synthesizer to figure out that the local pref should be lower on the provider than on the customer session. That's kind of like the idea. And you would like the synthesizer to discover that without having to figure it out yourself. So the problem exactly is the following one. You want to find a configuration which satisfies the specification for all the environments, all of them. So in order to solve this problem, we kind of like need to make now the configuration parametric. So this morning, when we looked at this verification problem, the configuration was kind of like used in order to build the equations, okay? So all these sessions were automatically iterated over, and then we were essentially outputting equations based on the configuration, okay? Like A is connected to B with such weights, and this is like a customer link, this is an external link, et cetera, et cetera. So all that configuration was kind of like taken as input, and then equations were generated based on it. So now this configuration will be undefined. It will be another parameter, another variable, a set of variables in the SMT problem. And so the SMT will have to find solutions now also for the configuration parameter. So configuration parameters, typically we talk about link weights, route maps. So this is again what you had to configure this morning. We might also talk about BGP sessions per se. So which router should be connected to which router, that kind of things. So these are all parameters now that the SMT also need to assign values for. So it's a much harder problem now because you have way more variables that you need to figure out the concrete value for. So the way, like one way to go about solving this problem is that you can, of course, create symbolic variables for each possible parameter. There are a lot. We only saw a few. Then you write the equations in terms of these parameters. Then you let SMT do its magic. And then once you have like the actual values spit out by the SMT, you can build a configuration out of that directly. So here, for instance, coming back to our example this morning, we can essentially set the local pref, which is being set on these sessions as a variable cprof, and then have this variable here for that session ccust. And then we can write the equations now in terms of these variables. So instead of having concrete values in the equations, now we'll have extra variables that represent the concrete local pref that will be set. But it's not defined. It's not 100 or 200 anymore. It's now another variable that will be taken into account in the equations. So the equations are less defined than before. So we have to find a configuration that is satisfied, that satisfies the spec for all the environments. So this is also a big difference with respect to verification. So if you remember in verification this morning, we took the negation of the spec, and then essentially the task of the solver was to find one concrete assignment that was violating essentially the specification. So we kind of like, we didn't have universal quantifiers. We had like an exist quantifier, but we didn't have a for all quantifier in that formula anymore. We needed to find one concrete set of inputs such that the specification is violated. In synthesis, the problem is also harder, not only because there are more variables to assign values for, but also because the specification now needs to be satisfied for all the routing inputs. So we cannot escape this for all anymore. We really need the configuration to work for all the possible different values. We just don't want one single concrete values that works for one environment anymore. So this is something that typically SMT are struggling a lot with. So when you ask SMT to solve formulas with universal quantifiers, they have a hard time doing it typically. So here again, like the for all pertains to all the routing inputs. And so we want the configuration that fulfills the spec for all these possible routing inputs. So a naive way that SMTs can go about solving this problem is kind of like verifying that the specification is satisfied for a given configuration for all the possible inputs, for input 1, input 2, input 3, all the way. So of course, there can be exponentially many routing inputs to consider. And so this makes the problem completely explode. So it's already a very hard problem to solve when you only have an exist, but when you have a for all, now you have to consider all the possible environments. So that doesn't work. If you try this, it will never scale. So what a lot of synthesizers are using is a more, let's say, constructive approach in order to solve this problem. And this is also applied in program synthesis. It's a very common technique that I will show you now. And the idea is to kind of like try your luck, in a sense, in figuring out a configuration which only works for a subset of the environments. And then you do that in the first stage. And then you verify, you use a verifier to verify that your configuration works for all the environments. That's kind of like the loop that synthesizers use. So they, again, like the trick is to find a config that only works for few environments, and then verify that that configuration works for all the environments, instead of like directly finding a config that works for all the environments. So synthesizers, they use verifiers as a building block. It's kind of like a loop which is built around them. And of course, the idea is, okay, what are the environments that you should consider for like initially finding this configuration? And how do you kind of like make progress in this loop and kind of like leverage the verifier in the best way possible? So this is, I will go slowly and I will give you example now of this technique, which is known as counterexample guided inductive synthesis. So it's counterexample guided because we use the counterexamples provided by the verifier, and it's inductive because it proceeds in rounds. So we'll grow the set of environments bit by bit, using the counterexample that we get from the verifier, and that will help us kind of like guide the synthesizer towards a configuration that works for all the environments. That's kind of like the idea. And this technique was developed for program synthesis. It was one of the milestone results in the last decade that actually made program synthesis even possible. So program synthesis is facing the same problem. You want to design an algorithm out of a spec, right? You don't want to code anymore. And of course, the space, the universe of all the possible programs is gigantic, and you cannot kind of like explore it exhaustively. So they developed this idea of counterexample inductive synthesis that also relies on the verifier. So the idea, how it works, is that you first start with completely empty environment. And then you find a configuration that works for essentially an empty environment. And then you will get a configuration. And then you will verify that this configuration works for all inputs. If you are extremely lucky, so by chance, pure chance, you actually found a configuration that works, you're done. Because the verifier will tell you, yep, your configuration is correct. Most likely, though, you won't be correct. And so you will get a counterexample. So you will get a concrete environment in which your configuration is incorrect, okay? That doesn't meet the specification. So now you can take this counterexample, and then you can loop it in, and then give it back now to the synthesizer. So now your set of environment is not empty anymore. You have like one concrete example for which you want the configuration to be correct. So now the synthesizer will find a configuration. Of course, there is a process to do that for this environment, which didn't work before, and then you will again reapply the loop. And so you will give that to the verifier, and then you will ask the verifier, does that configuration work for all environment? And then the answer might be yes, in which case you are done, or it could be a counterexample, in which case you need to restart the loop. So at this point, I think it's good if I show you one example. And I will actually show you two examples. But I want to start with this one, which is a bit easier, perhaps, to understand, because it doesn't really relate to BGP, but it relates to shortest path algorithms. So the problem is about synthesizing weights in a network, in a graph that relies on shortest path algorithm, like Dijkstra, for instance. And you want to synthesize the weights so that you kind of like imply some given forwarding path. So for instance, let's say this is the initial configuration. As you can see, all the traffic in this graph is between A and C is forwarded along the direct edge. And let's say that for performance reason, you would like the traffic to be load balanced between A and C. So you would like the traffic now to go alongside 2 paths instead of 1 path. So essentially, in order to solve this problem, what you want is you want now 2 paths that have the minimum cost instead of just 1. And then protocols like OSPF will automatically start to spread the traffic onto these 2 paths. So essentially, we need to find the weights so that these 2 green paths have the minimum cost amongst all the possible paths. So what should be the weights for this to happen? Well, if we apply the technique that I was giving you before, well, first, let's say naively, like if you want to build a synthesis procedure that does that, using SMT, for instance, you can write these equations as such. So what you want is, you would like, so you consider all the paths between A and C that are not part of the requirements, okay? So for instance, this is a path which is not part of the requirement, this is a path which is not part of the requirement, etc., okay? So what you want is all these paths that are not part of the requirements, you want the cost of these paths, x, to be strictly greater than the cost of the 2 green paths over there, okay? And you also want the cost of the 2 green paths to be equivalent to each other. So these are the equations. You want the cost of AC and the cost of ADC to be equal, and you want all of them to be less than x, where x is the set of all the other paths. So if you, and then you want to give that to a solver, then you press solve, and then you get weights out of that. So if you do this and you give that to an SMT solver, by now you should be able actually to write these equations using Z3. You can do that, it's very easy. And you press solve, and then you will get weights out of them, and it will be correct in this case. The problem though, and I'm guessing like the more theoretical savvy person here in the room will realize that here I'm iterating over all the possible paths in a graph, essentially between 2 nodes. And that can be exponential. There can be an exponential number of paths between 2 nodes in a graph, at least in theory. So essentially, you can end up with a really large equations to solve, and then again, like solvers will struggle in this sense. So this is where, in order to solve that problem, you can really apply Segis almost verbatim there. So the idea is that instead of enumerating all the paths and then putting them into the equations, you will only enumerate a subset of them. And then you will, instead of considering all of them, you will consider a random subset of them, and then you will synthesize the weights only considering this subset of them. So this is fast because you can really bound the number of paths. If you tell me you can consider maximum 100 of them, I can just enumerate 100 paths, and then I can synthesize weights against these 100 paths, and then I'm done. So you can really control the time it takes for doing this step. But of course, you can be wrong because you don't consider all the possible paths, you only consider a subset of them. And so how do you do the verification step? Well, it's very easy. You run Dijkstra on the graph, and then you see whether the shortest paths that you have are actually meeting the requirements that you had in the first place. And running Dijkstra is very efficient, even in a very large graph. So you can check using Dijkstra that the weights you found are actually compliant or not. And if not, then you know a counterexample. You know one example of a path which is not compliant that you can then add to the set of paths that you're considering, and then you can reapply this loop. So let me give you an example here again. So again, the synthesis procedure is now considering only a subset of paths, and here we'll only consider one of them. So we'll only consider the paths A, B, D, C, okay? So we'll write the equation only with respect to A, B, D, C, and nothing else. So for instance, we'll not write the equation with respect to A, B, C, which is another path between A and C. And then we'll, of course, ask the solver to solve the equations, but only considering ABC as the path. And then we'll ask the solver to solve. So now we might get, for instance, this path as a result. So these paths, these weights as a result. So these weights, they meet the requirement. So they meet the requirement because we have these 2 green paths that have the same cost, 300, okay? And 300 is less than A, B, D, C, which is 150 plus 300 plus 150, which is 600. So it's perfectly valid, okay? We are like compliant with the requirement here. But if you run Dijkstra in your head, you can quickly see that the shortest path between A and C here is this path over there, A, B, C, because the cost here is 250, which is less than 300. And the reason why the solver got it wrong is because we didn't consider all the possible paths. So it's actually logical that it got it wrong in this case. So the actual path is this one. So this Dijkstra, again, can tell us very easily that this is the actual path, so n log n. And so we can then just union that path that we get into the sample path now and repeat the operation one more time. And so when you do that, we actually found that this converges in few iterations. So we only need a few counterexamples to actually find a set of weights that work in practice. So this is one example of a Segis loop applied to the problem of synthesizing link weights in the shortest path routing algorithm. So, of course, you want to do that not only for shortest path, but for instance, you want to do that also for BGP. Okay, so you want to do that for any possible routing algorithms that are out there. So if you think, for instance, about a problem before, like same problem as this morning, we would like to figure out, or like the synthesizer would like to figure out what is the relationship between cProv, which is the local pref on the provider link, on the provider session, versus CCust, the local pref on the customer link, in order for the specification prefer route from the customer over the route from the provider to be true. So you can think of the space as such. So on the x-axis, you have the local pref CCust. On the y-axis, you have the local pref cProv. And essentially, the space of configuration that work is here in green. So it's the set of configuration where the local pref of the customer is greater than the local pref of the provider. Then you have a line here, which is the local pref is exactly the same. And then all this part is the wrong part. This is where the local pref of the provider is greater than the one of the customer. So we can apply the same idea, the same Segis loop. So initially, we don't constrain anything, and we let the synthesizer pick local pref at random. And so, for instance, it might end up picking up points here with local pref for the provider 200 and local pref for the customer 100. So if you give that to the verifier that we use in the morning, of course, this is incorrect, right? And so the verifier will return you a counterexample. For instance, like we saw in this morning, it can return you a counterexample here where you can see that the provider route has an AS path which is greater, and then the customer route has an AS path which is shorter. And so here with this local pref and this counterexample, the specification is violated. Okay? Again, it's violated because the preference is the first criteria, right? And so here you assign a higher preference to your provider route. So now what you will do is you will feed this back into the synthesizer, and you will ask the synthesizer to figure out a configuration that works for that counterexample in addition to any others that you may have found before, but here there is only one. So you need to find now a configuration that works for that example. So here, what you should realize is that by asking now the synthesizer to find a configuration that works for that counterexample, automatically exclude the red region. Because the counterexample, as you can see, the AS path of the customer is shorter than the AS path of the provider. So the only way that we can have this configuration work is by either having the local pref to be equal or the local pref to be greater than for the customer. So by kind of like design, this counterexample exclude any values of the local pref that are in this triangle here, this red triangle there. But it doesn't include this line. And of course, it doesn't exclude the green part because that's the actual part which is correct. So then we add this counterexample back in, and then we ask the synthesizer again to figure out the value. And so now, with this counterexample, the synthesizer might give me the same local pref, 100, 100, for instance. So that works for that counterexample, right? So again, if you have the local pref, which is the same for the provider and the customer, and you have this counterexample here, the customer route is preferred, okay? It's perfectly okay. So it makes sense that the synthesizer can return me this value over there. It is correct for that environment. The problem is that it's not correct for all the environment, right? If you ask now the verifier of this morning to verify that config with 100, 100, it will return you another counterexample now. And now this counterexample is really the one we saw this morning, where the AS pass of the provider is of length 1, and the AS pass of the client is of length 3. So here, if you have the same local pref, 100, 100, but the AS pass of the provider is shorter, then the provider route will be preferred. So that counterexample, x2, is kind of like preventing any values alongside this line now, okay? So x1 excluded this part, the red triangle, and then this x2 is kind of like excluding this line over there. So now if you repeat once again this loop, and then you ask the synthesizer to find a configuration that works for both this counterexample over there, then now the only solution is actually to find a configuration in which the local pref of the customer is higher than the local pref of the provider. And then the loop finishes, okay? So it's kind of like the same idea of like calling the verifier multiple times and then learning from the counterexample and then kind of like iteratively figure out a way towards a correct config. But here it's applied to BGP, before it was applied to shortest path algorithm. So that's essentially the intuition of a synthesizer, which is based on Segis. We have actually worked on that problem quite a lot. So we have like multiple papers on this. So one here, which is really a direct application of what I've just shown, it's called NetComplete. And the idea in NetComplete is that we allow operators to give us a sketch of the configuration, so a skeleton of the configuration, and then the synthesizer will fill in automatically the skeleton. So that's, we found that this is a good way to kind of like let the operator control the output of the synthesizer. So the problem with synthesis, program synthesis, is that if you don't give any control to the operator, the configuration that it can synthesize might be completely crazy. And so it was a little bit the same problem as when people were still coding in assembly language at the very beginning, like, I don't know, like 25 or 30 years ago. So when people were coding in assembly language, and or like even more than this, yes, 50 years ago, I guess. So people 50 years ago were coding in assembly language, and then C came, and then there was a compiler that was able to produce, using mechanics rules, essentially, it was able to produce automatically assembly code. The problem is that the assembly code that the compiler was producing was very different than the assembly code that the human would write. And people were not trusting like the original compiler, right? They were actually very against the idea of like having this thing being automatically produced because they thought that they were doing it better. Of course, they got it wrong, right? So nobody, or very few people nowadays code in assembly, except when you are really caring a lot about optimization of performance. So most people don't even know how to code in assembly language anymore, right? So you, I mean, most people don't even know how to code in C anymore, right? So you see that this problem has been increasing now in complexity. But we observe the same discussion when we approach operators with this idea of synthesizing their config, because for them, they were very, let's say, doubtful of the fact that this configuration we were producing, even though they were proven correct, were actually working, because they were just very different from what they were used to do. And so the way to approach this problem is to say that instead of like finding any configuration that works, we actually want to add an extra constraint here, and which is to find a configuration within a space that actually makes sense operationally for you. Yes, question?
I have another example on this slide, content management systems for websites. Like we used to do the HTML in the editor.
Yes, yes.
And then the content management systems came along and took over. And it's impossible to mix the two because you cannot do something by hand.
Yes, yes.
That the CMS didn't do right. Now the question here would be, what about the interface to the rest of the system? Can you isolate it well enough
When you say with respect to the rest of the world, what do you mean exactly?
Well, to this, I don't know, think of 5 ISPs in Switzerland, but not
Sure,
all
sure,
of them
yes, yes.
using this, and how do they deal with the others?
So that's the, so the idea here is indeed we synthesize a configuration for one network, okay, not 5 networks, but like the inputs of the others, they are taken into account, right? So this is the constraints that are applied on the routing inputs, okay? So you can have Swisscom synthesizing a configuration given some specification about what Deutsche Telekom will advertise to them and ensure that their network will work independently of that. So they can actually represent the outside world through these routing inputs, and they can even leave them completely symbolic, which means then that you want the configuration to be correct independently of what you receive from the external world. But it makes little sense operationally to imagine that you can configure another network which is not under your control, administratively speaking. But BGP also is confined within one network, right? So you configure all your internal routers and the session here, but you never configure the other side's router. So this is kind of like independent networks are configured independently. Yeah, so that problem did not materialize yet. But of course, if you were to consider more centralized routing, then this would be something that you would need to take into account, yes. But so, all this to say that this paper is kind of like taking the feedback of the operator into account, right? They were telling us, we don't trust your synthesized configs. We want our configurations to look like ours. And so that leads to kind of like now workflow in which we can start from a configuration which is existing, but incorrect. And then you can poke holes in it, and then you can ask the synthesizer to fill in the holes so that now the configuration is correct again. So you can use this as a basis of like configuration repair, where now the problem is figure out where to poke holes and then call the synthesizer on these holes in order to make the configuration correct. So there are people who have been building this on top of our work over there. Another big advantage of this approach, which was another objective of ours, is that, of course, if we have a skeleton, we only need to find configuration within the skeleton. So we have like a much smaller space typically to search versus the universe of all the configurations that are possible. So it was also a way for us to reduce the search and kill 2 birds with 1 stone, so to speak. The more recent work, so this is kind of like my first ML paper since ever, actually. So this was a paper at New Rips in 22. And it's kind of like, I mean, the idea was essentially to try to avoid having to write all these equations in the first place. You know, like, I mean, you didn't need to do that this morning. It was given to you. But it's hard to write these equations, and you can get it wrong, which leads to all these problems that we have found in existing verifiers. So we said, okay, can we hope to have a machine learning algorithms actually figure out how to configure a network? And so it turns out that nowadays, there are many platforms that allows you to virtualize networks. So you can run virtualized networks, you can run them on concrete configs, and you can look at what is it that they output as a forwarding path. So essentially, you can get millions and millions and millions of examples of input config, output forwarding behavior, okay? And then you can train, of course, on your networks, for instance, to try to do this mapping automatically for you. So that's one step. So essentially, by doing this, you kind of like allow the neural network to simulate the behavior of a real network given concrete inputs. And then, of course, then you need to invert that in order to do the synthesis task, because in the synthesis task, you start from a specification on the output, and then you need to figure out the input. Okay, so in this paper, we show how one can do this. And that was a nice paper, but I must say it's only get it right in 92% of the cases. So it's not yet complete, okay? So unfortunately, Like there are some specifications for which we cannot find a solution. So we cannot find a configuration. Even one exists, then the machine learning model was not able to find this configuration in 8% of the cases. So not yet perfect, but it was a first, let's say, trial. And we were still happy with the fact that it got it right in 92% of the case, without any equations to write, right? It was just like input, output that could get done automatically, okay? So that was nice because it takes a PhD student a semester to actually write these equations. So it's really not easy. All right, okay, so perhaps I want to now take a step back and still, I mean, I haven't talked a lot, and I won't because I don't have the time, about how exactly the synthesizer is figuring out this configuration. This is actually quite intricate, so I won't go into the details there. I mean, if you are interested, of course, we can discuss about this later. But now what I want to kind of like explain you a little bit is how by slightly changing the problem, we can end up solving many operational scenarios that are relevant for operators, different ones. And so, and that led to also many different papers. And so I kind of like now want to expand a bit the horizon and show you other type of works that we have done recently in that space. So one problem is the one I've mentioned just before, is the problem of repairing configurations. So here the analogy is I give you an algorithm, the code of an algorithm, let's say it's a sorting algorithm, and there is a bug in it. So it's almost correct, but sometimes it gets wrong. And then the problem is how do you repair that algorithm, okay? So it's an easier problem in a sense than the problem of like figuring out the correct algorithm from the get-go. So you have the exact same problem in configurations where you have an existing config, it's incorrect right now, and then you want to figure out a fix, a patch to that config. So this is the problem of configuration repair. We solve that problem using NetComplete, as I said, like by kind of like being smart in where we put holes in the configurations. So we remove pieces of the config, and then we ask the synthesizer to fill in these pieces and see whether it can do that. And if not, then we poke holes elsewhere. And of course, the bigger the holes, then the more of the config you have to synthesize anew, okay? So you want to be, let's say, smart in where you poke, and you want to be small in how you poke as well, so that the synthesizer is faster. So this is the problem of configuration repair. Yes, so configuration repair, you can, well, I guess this is what I just said. So the open research question, which we only have partially solved, is again like where to poke these holes and figure out which parts of the config you should modify. Other synthesis problems that are, to my knowledge, not solved yet are the ones that deal with optimization, performance. So you would like now to synthesize a configuration that, for instance, minimize the maximum load in your network. So now you have a performance objective that pertains to, for instance, the amount of traffic that goes alongside each link, and you need to reason about that. And then you need to figure out the config that will minimize that. So now it's really kind of like solving an optimization problem where you have an optimization objective which is given to you, minimize resource, maximize performance, and then you want to figure out a configuration that does that. So the big problem here, and I think one of the reasons it isn't solved yet, is that in all the examples we were discussing so far, there was an implicit assumption that I've not mentioned, but that all the destinations are independent from the others. You know, like in the network, you have prefixes, and the way you route towards prefix 1 is independent that the way you route from prefix 2, like in the configuration at least. So in BGP, it's prefix-based. So BGP computes on a per prefix basis. It doesn't care about more than one prefix at a time. For performance, when you think about load on a link, you need to consider all the destinations at the same time. You need to consider all the prefixes that are crossing this link. You cannot consider them individually anymore. You need to kind of like do the joint problem, the joint optimization. And so that makes now your model not per prefix, but kind of like all prefixes at the same time. And so that makes it very hard to scale. So there is an kind of like an open question here, which is how to scale synthesis to consider not one destination at a time, but many destinations at a time, possibly all destinations at a time. And you will need to do that in order to solve performance problem. So that's an open, completely open problem. I think now people are kind of like moving towards that. You can see more and more initiatives. First in verifying performance properties, and also, of course, once you get the verification done, you want to synthesize after that. So that makes sense that there is a progression there. The community first looks at verification, and then after it looks at synthesis. Yes, so in case you care about complexity theory, we actually had a very theoretical paper this time on evaluating the complexity, the runtime complexity of many of the synthesis questions. So here in this paper, we essentially prove, perhaps unsurprisingly, that most synthesis problems that you may think about are actually NP hard. But it's not a conjecture anymore. We actually have the proof. We have the reduction. And if you are interested in that, I would invite you to actually check this paper that we published at ICMP 2 years ago. So these problems are clearly hard. It's not like they look easy because the SMT sometimes get it, but as you scale the network and the network becomes larger, at some point it will stop working, and then you need to do other tricks in order to get it there. And now, of course, we know why because of this. By the way, even like figuring out, I haven't mentioned that, but in the verification question, like for instance, the problem of like figuring out whether a network will ever terminate, it's kind of like equivalent to the halting problem if you think about it. So we have another paper, which was a very nice paper, I think, in which we actually showed that you can emulate a Turing machine using only BGP routers. And so that means, it's a bit meta again, but that means when you do that, assuming that the BGP network can go infinitely large, then essentially you can have an infinitely large Turing machine with an infinite tape. And so you end up with the same halting problem there that applies to a BGP network. So it's normal that a lot of research about deciding whether a network will terminate is actually very hard. It's because it's the same problem as deciding whether a Turing machine will actually terminate. And if you make the Turing machines finite in size, then the problem becomes p-space hard, not Turing, Turing complete. But so all this to say, this is only for the very specific questions of convergence, okay? And so here, in that paper, we also included other properties, other specs, and studied the problem of like synthesizing configurations for them. So if you are theoretically inclined, I think this could be a nice bridge between the two worlds. All right. Yes. Yes, so perhaps I would just skip that, and I will speak a little bit about this thing. So right now we have been synthesizing configurations. So we had like topology, specification, environment as input, and then out we are getting a configuration. But this is not the only thing that you may want to synthesize. And so another problem that networks, that we realize as we're working on this and discussing with operators, is that we were telling them, we have a solution to your problem. You give me your specification, and then we will give you a configuration which is provably correct. And then they were looking at us, and then they were telling us, we do not know the specification of our network. And then we realized that actually writing the specification, it's hard in the context of an algorithm, but it's also hard in the context of a network. And one can say it's perhaps even as hard as writing the configuration in the first place. And so people just do not know the specification that they're actually implementing on the top of their head, and they certainly cannot express these specifications through a formal language, which is kind of like requires for like a solver like Z3 to actually work. You could actually see that this morning as well, like the last specification, which is still very simple, right? We only wanted like the customer route to be preferred, except when the community 5 was set on the provider routes, and we already got like a decently long like spec out of that. So just think about the specification that a network like DT would actually see. It's of course much, much larger. So when they told us this, we realized, yeah, that's a problem. So can we actually mine the specification out of the network now? So what we thought about is, okay, DT, the operators, they cannot tell what is the specification, but they do have a configuration. I mean, they have a configuration which is running right now in the network. It's supposedly correct because that network has been running for a while, so you can hope to actually get the specification out of that, and then you can start to work from there, right? So if I can, given a config, extract the spec, then what I can do is delta reasoning. So you give me the configuration now, you make a change, and then I extract the spec before the change, I extract the spec after the change, and now I can explain to you what has changed in your network. I can give you an explanation of the delta between the two. And this I can do at the specification level. And so that led to this paper, config to spec, which, as the name indicates, mines specification out of concrete configurations. And so that kind of like solve another problem now, another operational questions. So we can use this tool to get the specification, and now once we get the spec, we can modify the spec, and then we can generate new configuration with synthesis after. So that's kind of like closing the loop there. So that, it's also, I think, a nice paper, and that paper kind of like also combines ideas from verification and synthesis together. So it's a nice story. But, and this is how I could answer this question that I've mentioned this morning. So we realized when we were mining the specification of existing networks that these specs are extremely large. So these 10,000 predicates, this is actually a spec that we mined. And that was not even like in a large scale network like Deutsche Telekom. It was in the provider of ETH. But it just shows that we kind of like need better ways to represent the specification, that this very low level language that we have now. So now these are like questions that we're exploring in the group is what kind of languages? These are kind of like programming language question now. Like can we imagine having a high level language to express specification instead of like talking very low level? How can we abstract away these predicates and kind of like what is the Java or C++ equivalent if the spec is kind of like seen as the assembly language? So, these are like open questions that, as I said, we are looking at now, but we don't have even like a paper in preparation there. So we're just scratching the surface there. What is that? Yeah, so here it's another synthesis question in which we ask the question of like evaluating the robustness of a network. So it's kind of like asking how many counterexamples there can be for like a given violation. And that gives you an idea, kind of like a proxy for how robust your network is against variation in the environment. So this is another problem that we look at. So I think this is the last one that I want to mention, and this one we've been working a lot on it. Actually, my PhD thesis was exactly on that problem as well, but back then we did not phrase it in terms of synthesis, but now we have. But the problem is about reconfiguring a network. So it's great to synthesize a network-wide configuration and then hope that you can push that in the routers, but that is also not really how operators work. So operators, they have like a large network running, and then they modify the configuration bit by bit, okay? So you end up with like a config, and then you have many deltas that are applied to that config, one after the other. And so in the case of a reconfiguration, you have an initial configuration, the one which is running now, and then you have a final configuration, which is the one that you want to run after. And then the problem is to figure out in which order do you need to reconfigure the element in your network in order to guarantee the specification, not only initially and finally, but also in between the two, okay? So you want to guarantee correctness also as you're touching and modifying your configuration. And this is essentially a scheduling problem now. So you need to find a schedule of the reconfiguration operation such that you maintain correctness across each intermediate step. And you can phrase that as a synthesis question. You can ask, synthesize me intermediate configuration so that when I apply them one after the other, I actually guarantee correctness, and I also eventually reach the final configuration. It's kind of like the progression aspect. So as I said, we had a lot of research on this, and in 21, so 3 years ago, we had a paper, the first paper on synthesizing network-wide configuration updates, where we are able to figure out this ordering automatically. And then we had another paper in 23, so last year, also at SICOM, on essentially doing this problem, but also considering the transient state that are being explored by a network. So if you think about the network running a distributed algorithm, whenever you change a configuration, the distributed algorithm has to converge, okay? And as you converge, you might explore you might start to forward the traffic in different ways than the initial one or the final one. And so what we realized is that we were synthesizing a lot of intermediate configuration steps between initial and final, but we were not really reasoning about what the protocols were doing as we were applying this configuration step one after the other, transiently. We're only thinking about steady state. And so in this paper, we actually also considered that. So now I'm pleased to say that we can really reconfigure network now from the initial state to the final state, guaranteeing correctness all the way. So that's kind of like the final piece of the puzzle when it comes to reconfiguration. And we did that considering BGP. Now we're also thinking about how we can generalize this to other protocols. Yes. So I will stop here. I thought I would be faster, but I was not. But at least I'm on time. So it's 5:29, 28. Any burning questions before we switch to presentations? There is another break. Okay.
Yes, we can ask more questions there.
Yes, yes. But so if you have questions, feel free to find me at the break. Otherwise, I'm guessing we will put the slides online somewhere.
Yes.
And yeah, so I hope you enjoy this very quick intro to very fast synthesis. And yeah, all the best.